This LTO-related oral history complements another LTO-related oral history entitled IBM Tape History, Session 4, LTO Virtual Company Panel. John Teale, one of the panelists in this oral history, was also a panelist in the previous oral history. This interview will involve Messrs. Tom Albrecht, Bob Biskeborn, Tim Chainer, and John Teale regarding their contributions to key technologies that enable the family of linear tape open LTO tape drives. No one has yet invented data storage technology that could replace magnetic tape recording for archiving of information. Magnetic tape continues to offer, by far, the lowest cost of data storage. Until recently, this product space used two classes of devices: digital linear tape, DLT, and LTO. However, LTO proved to be superior, and as of 2019, LTO has achieved 100% market share. The success of LTO is based on dramatic increases of data track densities achieved via use of time-based servo, longitudinal position encoding, Flexure-based Actuators, flat head-to-tape interfaces, and adaptation of 3 generations of film-based magnetoresistive disk heads. Impetus for these developments originated in the early 1990s in an IBM research effort led by Dr. Jim Eaton, which was funded by IBM Tucson. This oral history records the contributions of the individuals responsible for the invention through prototyping of these technologies. So, John, I would like to ask you to lead with a brief summary of, and all of you then follow with a brief summary of your personal backgrounds.
Okay, good day. As Chris mentioned, I was part of a couple of other oral histories, and I talked about my background extensively in some of those, so I would refer you to those if you're interested. For the purposes of this meeting, where we're focusing on research, IBM research contributions to the tape industry, suffice it to say I was a longtime leader of the IBM tape development team in Tucson, Arizona. I retired in 2009. I still live in Tucson, and I will be providing background and context for these gentlemen here.
Tom?
All right, I'm Tom Albrecht. My background is I grew up in a small town in rural western Wisconsin. As a kid, I liked to do a lot of hands-on, you could call it technology if you like, but mechanical and electrical things, repairing things, building go-karts. But most of all, I liked making electronic circuits and doing things with that. That ended up being useful training for my career. Also ham radio, I did a lot of that in those days. Went to college at a liberal arts college in Minnesota called Carleton. And that was also useful in my career development in terms of really learning to speak and write clearly and think critically. And also I was a physics major, so that helped establish some of the technical knowledge needed for the career. Went to Stanford for graduate school. Was originally interested in free electron lasers. That's what I thought I was going to go to Stanford to do, but I got there and I wasn't as comfortable with the group doing that work, so I was looking around for a group that I thought was really doing something very interesting and a place where it looked like the students were having fun. And I ended up then in Dr. Cal Quate's group, working on scanning tunneling microscopy and atomic force microscopy, which at that time were really hot fields, and that turned out to be one of these deals where you're at the right place at the right time, and you maybe end up getting a little more exposure than you really deserve just because the field is so hot. Anyway, that was a lot of fun. Got to work with a person who later won the Nobel Prize for inventing the scanning tunneling microscope and so forth. After Stanford, then this sort of notoriety that had come from working in such a well-known field sort of got me in the door at IBM, and there were groups interested in hiring me. and came down to Almaden. Actually went to Rochester too, I think, and a few other places. But came down to Almaden, visited several groups, found some that I liked, but I did not talk to anybody in tape at that time. However, for whatever reason, Jim Eaton got wind of the fact that I had interviewed there. And he said, oh, I would have liked to interview that guy. I'm not sure why what connection he saw or what he was looking for. So he came up to Stanford and interviewed me there. And it was sort of an embarrassing thing where, getting a job to me was very important at that time. And I actually forgot that Jim was going to come and visit that day. So he had to kind of hunt me down and find me. Very embarrassing for me. But then we hit it off well. He had his little satchel. I bet you saw that same little satchel with a few motors in it. And he talked about the scaling of inertias. And he had this grand vision how he was going to make. I think he was mostly interested in fast access. Yes. Among other things, which turned out not to ever really be the main deal for tape. But in any case, he was very interested in that. And so when I got to IBM, I did join the team at Almaden. I didn't decide on just one thing. I actually worked on 3 different projects simultaneously. I stayed with scanning probe microscopy, working a bit with Dan Ruger. And then John Foster sort of had me pulled into some hard disk drive work that he was doing. And Jim Eaton had me working on tape. And tape was very interesting because it was this mix of mechanical and electronic and software and physics. Everything is in tape. And it suited me well. Having a bit of an interest space in mechanical engineering as well as electrical engineering and physics. I really enjoyed all those aspects of tape technology. And although I actually never reported into the tape organization, Jim was never my manager, I kept this thing going on the side for like 10 years, stayed involved, sort of culminating at the end in the LTO standards committee stuff and so forth. So that's how I got involved in tape. I did end up working on lots of other things in my career as well, many things in hard disk drive that I worked on over the years, sort of culminating in a 10-year leadership of IBM's patterned media project, which turned out to be a bust in the end, but that was really a highlight of my career to be able to lead that project for 10 years and really do cutting edge work. In the meantime, now I've moved on to a small startup company, Molecular Vista, which takes me all the way back to my grad school roots, so I'm now back in scanning probe microscopy. So in a nutshell, that's where I come from.
Out of curiosity, who was your actual first manager in Almaden? Of the people you work with?
The first one I signed up for full-time, I believe, was John Foster.
Okay.
So, yeah. But I kind of had a deal with John that I could keep on working on tape. And that worked out okay.
Good, good. And if I'm not mistaken, in your hard drive stint, did you have something to do with the micro drive?
Yeah, quite a bit. Yeah. So Tim Riley and I did a lot of work on the micro drive, and that was a fun project as well. Another one that had some very interesting mechanics in it, to make this very, very small package. In the end, that was completely supplanted by flash memory, but it was a lot of fun while it lasted, and yeah, good project.
It got a lot of attention in the industry. Thank you, Tom. We'll move on.
Hang on.
Yeah, go ahead, John.
Could you say a few things about your family?
Oh, so my father was a medical doctor, and but he liked hands-on technical work himself also. So he was always into repairing appliances and so forth. I just remember, like, when we got a new dishwasher, he sold the old dishwasher to one of the office ladies at the clinic where he worked, and then along with that, we repaired it for the next 10 years. We'd go over to her house and fix that old dishwasher. So he sort of also played a role in getting me interested in things electronic and mechanical, even though that wasn't his career at all. So yeah, but small town western Wisconsin, dad a doctor, mom was a stay-at-home mom, and I had 3 brothers.
And you're married?
Yes. And 3 kids now, 17, 18, and 19 years old.
You have your hands full, right, at this stage in their ages.
Sure. Yeah.
Tim, how about you?
Okay, so starting at the beginning.
Yep.
Family background. So I grew up in New Jersey and went through the whole New Jersey school system. I grew up in a small town called Emerson. And after that, I went to a small engineering school in New Jersey called the New Jersey Institute of Technology. And while I was there, I got interested in physics. I actually changed my major from mechanical engineering to engineering science. And then I went to Rutgers University, where I got my PhD in experimental low temperature physics. So it was quite a range. Continuing on in terms of growing up, you know, we were raised, I was raised by the greatest generation, right? And this generation was amazing. They could fix or build almost anything. So I had some incredible examples. My father was a textile chemist after getting out of the Army, and my mother was a nurse. I had an uncle who worked in the oscilloscope division of Dumont Labs way back in the 1950s, and my grandfather was a machinist and a model maker. So it was surrounded by all this innovative people who could tackle almost any problem. The first exposure I had to technical innovation was in the early 1950s. Above ground pools were just starting to begin, where your middle class people could actually have a pool in their backyards, and they were above ground. And at that time, there was no infrastructure to support these pools. So my father and uncle actually teamed together, and they built their own water filtration system for the above ground pool from a 50-gallon drum and a washing machine motor and pump. And they created a bunch of layers of gravel and sand and you know, various things to do the filtration. And my father, being a chemist, you also have to go back to that time. There was no like pool chemicals available. So he would go to an industrial supply and pick up chlorine and deal with the pool chemistry and do his measurements. So that was a pretty innovative experience. And then my uncle, who had worked in the oscilloscope division, actually had an electronic shop. And that's where I first became exposed to electronics with my cousin. I think the first time I ever turned on a soldering iron and saw a transistor and resistor, and we started building things. And eventually, you know, went on to build Heathkit, which you probably remember, when you could build your own little tools. And I built a Heathkit voltmeter and those kinds of things. Let's see how far, continuing on, what I knew from a pretty early age that I liked to take things apart and was probably interested in engineering. I think my parents recognized that after I took apart most of the appliances in the house, they got me a Gilbert Rector set and a home chemistry kit, which we probably all had as kids, right? And luckily we didn't blow ourselves up. And I think they wanted me to stop taking apart any appliances after that. Continuing on then, when I got to around 12, I think my first real system integration engineering project was to build a mini bike from a bicycle frame. So that was the first time that I ever actually looked at an entire system and tried to build it with a frame and an old lawnmower engine, and actually had to make some engineering drawings. I had to find all the components. We found a local welding shop to relocate the center bar. And I think I did my first engineering drawing, which I gave to my brother, who built the axles in the metal shop in high school. And so after taking a few spins around the block, I knew I was hooked, and I was definitely going to go to engineering school. You want me to continue on into school?
Yeah.
Okay, so
fill in the details.
Okay, so I started in mechanical engineering, and but what happened is I kind of quickly got enthralled with physics and, you know, learning about the mysteries of the universe, in particular quantum physics and special relativity. The idea of superconductors and superfluids were quite amazing. And so that kind of supplanted my interest at that point in engineering. And that got me off into going to graduate school and getting a PhD in physics. And my thesis work actually turned out to be on superfluid helium-3. Going back, which actually a Cornell group won the Nobel Prize in 1996 for that discovery. It was known that helium-4, which are bosons, would be superfluid, and they would have these amazing properties that they could flow without resistance. But helium-3 is a fermion, and therefore would not go into this Bose-Einstein condensation. It would have to follow more like the BCS theory of superconductors, right? They would have to form up pairs. So it was hypothesized that helium-3 should become superfluid based on the BCS theory. My advisor actually worked for John Wheatley here down at UC La Jolla, and they were part of that race to find the superfluid properties, and they were just edged out by Cornell. So Cornell saw the phase transition, but John Wheatley, who was a luminary in low temperature physics, and my advisor, Harry Kojima, did the first definitive experiment to prove that it actually had superfluid properties by measuring the speed of fourth sound, which is a sound that exists in superfluids. So that kind of was interesting to realize that there was this amazing race for Nobel Prize, and my advisor was very close to that, so that got my interest, and that's when I went into helium-3, low temperature physics research. And I worked at around 2 millikelvin. And now it's interesting that a lot of the technology in low temperature physics, which were dilution refrigerators, that could produce temperatures, continuous temperatures down to 10 millikelvin. And John Wheatley was one of the luminaries in that field in advancing the state of the art. But now those refrigerators are used everywhere for now quantum computing devices. And they're kind of standard. You always see these chandeliers, they call them, which are, in low temperature physics, we call them cryostats. And now they're ubiquitous. So dilution refrigerators are now becoming ubiquitous as every group starts looking at quantum devices. So it's an interesting application of really what was a race for absolute zero. So that's how I got into superfluid physics. I could continue on how I got all the way to IBM? Or?
Yes.
Okay.
We want to know how you got here.
All right. So while I was at Rutgers doing superfluid research, I met a postdoc, Tom Worthington. And Tom was also a low temperature physicist, and he had joined this new exciting group at IBM Research. And when I was looking for a job, Tom told me, you ought to come here to IBM. This place is amazing. There's a bunch of innovative researchers, and in the afternoon they are a bunch of rock climbers, and they actually climb the walls of the research center. And that got my interest. And so when I came to IBM to interview, I actually interviewed with two groups. One was the Josephson computer project, was actually looking at a low temperature device to replace the transistor, and I could have applied all my low temperature skills. But then I met Dave Thompson and yourself. And I guess I was more excited about joining the group that were climbing the walls and the exciting work that was going on in magnetic storage. So that's how I ended up coming to IBM. And actually, you probably remember my first project was the Hall probe magnetometer.
Yes.
Where we were going to measure the nickel thickness on a ceramic substrate. IBM was making these incredible 100 chips on a substrate, multi-chip module, which is really amazing. And I had to measure the thickness of the nickel film, which was on the order of the surface roughness. And you folks had invented the idea of, well, we could measure the magnetic moment. So I built an air bearing to fly a Hall probe magnetometer over the top surface. And that was also helped me realize my dream of computer automation. Back in low temperature physics days, the experiments were really arduous. Data taking would go on for 36 hours once you demagnetized your cell and started 2 millikelvin. I quickly realized that standing there for 36 hours taking data manually could easily be done by a computer. So I was really interested in computer technology. And when I came to IBM, the Hall probe magnetometer actually was automated by a Series 1 mini computer. So I was able to not only do that application, but realize my dream of computer automation, and that got me hooked, and I've been at IBM ever since. So.
Now, that exposure to the nickel challenge, right? It was an early exposure to semiconductor packaging. Have you worked in that some more?
Yeah, so it's funny because that was my first project in magnetic storage was, in fact, the packaging project. In fact, I recall many times where you cleared the way for us to get that tool actually onto the manufacturing line. And it was on the line and measures parts. And now many years later, after IBM divested itself from the hard disk drive business, I went back into electronics packaging and cooling. And I've been a principal investigator of 3 different government programs on basically embedded cooling in die, as well as data center energy efficiency. So I've kind of come full circle all the way back into packaging. So that's where I am now.
Very good. Thanks for that summary. Bob?
Sure. I was hoping to be much more terse. Kind of speed it along here.
But now?
No, don't take any shortcuts.
Well, okay. So actually, I was going to start with when I joined IBM, which was 1978, but I can look back. But let me begin there. I joined IBM in 1978. I have a PhD in physics from Columbia University, low temperature physics.
Oh,
My advisor was Bob Guernsey, whom you may have known.
I interviewed with Bob Guernsey. He was running that Josephson project.
Yeah. And so when I was in grad school, I was not really too sure about what I wanted to do. Did I want to go continue on in academia? Did I want to go into industry? What happened was there was a person at IBM, Larry Spector, whom I know you know, Chris, who was at the time a second line manager and was looking for people to join his group, which was looking at packaging considerations for multi-chip, multi-layer ceramic modules. And he contacted me, I interviewed, and thought it was kind of an interesting change from low temperature physics that I've been doing, which in my area was exploring superfluid effects in liquid helium-4, which is kind of mundane, but compared to liquid helium-3. But in any case, I accepted the position. It was kind of interesting that
was that in Yorktown or in San Jose?
That was in San Jose.
Okay.
I'm sorry, in San Jose. I'm sorry, Chris. That was in Fishkill.
In Fishkill.
I'm moving.
Yeah, no, because Larry Spector moved around too,
He
and
did.
I wasn't sure where did you connect with him.
Larry had been in Poughkeepsie, and then
Right.
he came to Fishkill, and then he went to Mainz in Germany, and then when he came back to the U.S., he came here to California, to San Jose, where he hooked up with Jim, which is how I wound up coming here. When when I was in when I hired into Fishkill, it's kind of interesting that Jim was running the laboratory at that time, which was the combined semiconductor and packaging labs. And so Larry was, very excited. Well, your resume would have gone up to Jim. So in a sense, Jim was in part of my hiring process. I don't really know. I don't think Jim ever said that, but anyway. So I had a connection with Jim and Larry, of course, early on in my career in IBM.
And which date was that? When did you join Fishkill?
I joined Fishkill in May of 1978, and I think at that point Jim had moved on, or was just in the process of moving to Yorktown, I believe it was, or to headquarters.
I think he moved
Yorktown
on to headquarters.
Yeah.
Yeah.
So in IBM in those days, I worked in packaging, and then I moved into the semiconductor lab, and then I worked on some interesting projects there. I got pulled back into packaging by a guy that I had met in my first couple of years in IBM, where his interest was how do we improve the thermal packaging for the multi-layer ceramic modules, something I had worked on only a little bit in my first couple of years. And anyway, he and I hooked up and came up with a scheme for doing just that. And eventually the scheme was adopted. And I think it's kind of interesting because when I got better acquainted with Jim, it turns out he was also very interested in the same identical problem and had come up with some schemes that were somewhat like what I had wound up doing, and we had great fun talking about that and debating what is the best approach there. In any case, what happened to my career in Fishkill is that it transitioned to San Jose in about 1990. This was the result of the outcome of the task force that Jim had set up in the late 80s, and I think I'm not really sure, John, of how it actually came to be, but it was decided to set up a kind of a tape head development group in San Jose, and Larry Spector was going to manage that, and I believe the Tucson management funded.
Yes, very early on we We're exploring, I think Fontana was involved, Bob Fontana.
Not in my.
Oh yeah, he was. Yep, at the very.
Was
very
he?
early times,
Okay.
He was part of it. Yeah.
If
No.
anything, that group was advocating a tape head concept that was way before its time, because it did end up being a lot like what we actually did. But it didn't come to fruition at that point in time, and I don't really know why. But yes, there was an effort here. Never really got too much traction,
Right.
but we were aware of it.
So Larry called me up one day. I was in Fishkill in my office, and hey, what do you know about tape and tape recording? And I said, not a lot. I had a tape recorder. And he said, well, he and Jim Eaton were brewing some ideas, and they wanted me to come out and interview, which I did, and got a job offer and took it. Moved to California in the late 90s. And
Before you go further, who was your colleague in Fishkill who worked on the improvements to the cooling of the multi-chip modules?
you might have known him, Joe Horvath,
Yeah.
Hungarian.
Yeah, yeah. I just
Very
thought since you
brilliant guy.
mentioned it, it'd be nice to
Yeah.
know
Yeah.
who
He
that
and I
was by
had
name.
it was just such a, it was a project that went on for several years. It was very consuming. I know you may have.
Yep.
Yeah, yeah, that was
Thermal
it.
conduction module.
Right.
Yeah.
It was just great fun, and it was great fun to. That's when I actually learned how to cause a revolution to occur, and once you have that taste, then you don't. That's what you want to do from there on out. But in any case, if that makes any sense, in any case, I hired out into San Jose, and I worked on some. Tape problems. One of them was studying some new films that were envisioned for possible use in tape heads. An example is a multi-layer nitrogenated iron-nickel iron film that was being looked at by some people in the hard disk drive business for improving the writing capabilities of hard disk heads as the hard disk media coercivity goes up, then you need heads that have more oomph to write to them. But we were interested in looking at those for the opportunity they may provide for tape heads, because they may be more durable. The idea being that nitrogenated iron is a tougher material than some of the other magnetic materials that were being used in magnetic heads at the time, such as permalloy and stuff. But so anyway, we were in that sandbox for about 3 years, and then the funding dropped, and John knows a lot more about that than I do. But the folks in that department were me, Dave Segal, Mara Stovek, who is now the head at Headway, the CTO in Headway. And some other folks, Tom Bolio, you may have remembered him, scattered. Most of us found jobs in the hard disk drive areas, which I did. That led to this. Maybe you're right, John. I talk, and I really.
No. You're doing fine. You're doing
okay,
fine. No.
No worry, Bob.
It's an embarrassment, but
No. You're doing fine.
Bob's plane never lands. So.
Right. Well, I know where I want to land when I take off, so that part's good. But maybe I don't call the airport ahead of time. But anyway, this is really a great part of this story. Dave Segal, who Larry had hired into this group in California, was a trained magnetician, PhD, and AA from CMU. He and I worked together in Larry's group. We scattered. He went into HDD. He then approached me one day with a story that, hey, somebody from the IBM tape head wafer line was in Fry's in Sunnyvale one day. And he encountered this little end display with a couple guys on quick drives. And he struck up a conversation with the two people there, both of whom I knew later. And it turns out that they, at that time, and this was 93, I guess, about 94 maybe, were looking for a way to build MR tape heads for quick drives, which at that time were just brass heads basically. They were the dominant provider of quick tape heads at that time. I think they had 90% of the market. And this person from the tape head wafer line, and which had moved from Tucson to San Jose in the late 80s, came to Dave. He knew Dave, and Dave said, "Well, let's see. Maybe there's something we can do there." So, and it turned out that we were kind of lucky because at the time the disk line in San Jose was under capacity due to lots of things taking place at that time. It was not a great period for IBM in general, I would say, from a business standpoint. There were a lot of changes taking place, and so a small group of people got together and went back to this company, which was Herald Data Analytics, and said, "Hey, tell us more." That led to us actually, for the first time ever, skipping about a year of effort here, building the first tape head, single track, quick quarter-inch cartridge, quick tape head wafers on the disk, on the hard disk drive line. So that was really quite fun and quite exciting. And I worked on various aspects of that, but it was only more obliquely involved until HDL needed some help in figuring out how to fabricate the heads. How do we lap them? What kind of contour do we put on them? And that's where I became more heavily involved. And that was successful enough that IBM funded it for about a year and a half. And eventually the plug was pulled on that. And I was told by my manager, Aaron Keeley, at the time, and I think, Chris, you were involved in some aspects of that.
Yep.
Yeah.
I remember Aaron. I remember so far everyone you mentioned.
Yeah, good. And so Aaron said to me, well, it was a kind of a sad day, no more quick. And there were, at that point, there were about a dozen of us working on the project. And she came to me and said, look, she's got quite a bit of money left over from that, probably a year or two of funding for a person, so stay on. And I said, well, what am I going to do? Can I do whatever I want? And she said, yeah, but you got to help me with some of her manufacturing problems. She was, I think, a third line at that time in charge of wafer and fab for the heads, the tape heads that IBM was producing. So I took, what I did was I took learning and experience that I acquired from my activities in QUIC and working with, it was really fantastic. I mean, I got a chance to work on magnetic design of heads to some extent, and fabrication and integration, and there was some interaction we had with Tucson, and HDL flew to Hong Kong a number of times as a part of that work. But one of the things that struck me is that so at the end of that, and this point of time where I now had some free time, if you will, I thought, well, look, I'm now convinced that we can build full-blown multi-channel Magstar type tape heads, not in the ferrite-based wafer line that was running parallel to the hard disk drive line in San Jose, but to build them right on the hard disk line, using all their full-blown processes. And furthermore, it seemed to me that maybe there's a way we can even use their fab process, and that was a little more tenuous, I would say. So the premise there was that could we use flat-lapped heads and make a good tape head bearing surface, doing that because we didn't want to do, HDD heads were flat-lapped, not contoured. So anyway, you know how it turned out, but I think along the way I thought, I can't possibly do any of this alone. I need a helper, and I didn't have any helpers. So I asked Erin if it'd be okay if I called Jim Eaton back from retirement. She knew Jim. I did. And I said, hey, Jim, are you interested in this endeavor? And he said, absolutely, you bet. And I said, fantastic. Come on back and let's have some fun together, which we did. And he told me later, it turned out that he was actually on his way to an interview at Hewlett-Packard in their tape division, and that I caught it just in the nick of time. But so he and I started a bunch of work together that maybe I'll talk about more when we get to that part. Prior to physics, my passion my first passion in life was butterfly collecting, and that stuck with me to about the age of 18. Passions change, but I was absolutely overwhelmed, consumed by that passion, and traveled all over the place. And I had and I joined up with other people. So, and that had some very good experiences. But my interests morphed from, let's call it natural history and biology, which required a lot of memorization, to, hey, in my thinking about the world, I'm thinking, well, chemistry is sort of an underlying layer behind biology. I became very interested in chemistry, especially theoretical chemistry and organic chemistry. And then I began to realize that underlying all of this, how atoms come together and create what we call chemistry, there's another layer behind that, which is physics. And I became very interested in that and math.
This is in high school already, or in college?
In high school.
High school, great.
And I wanted to say something that is off track, running off the rails here. So one of the things that I mean, and I probably really shouldn't be saying this, but one of the things that really have always been very interested in is the relationship, is really how mathematics is able to explain and describe the things we see in our world. And I mean, this is Galileo first was articulating thoughts like that, obviously. But there's a physicist, Max Tegmark. I don't know if you guys are familiar with him. So he's a physicist at MIT, and his thinking and what he's talking about, you can see his presentations on YouTube and stuff. But his idea of the world is that the world isn't explained. The universe is not explained by math. Mathematics is expressing itself in the universe. It's a really, really interesting idea. And so that, to me, when I heard that, I was telling everybody about this and how it so much resonated with the way I like to look at things. Not that I'm a mathematician, nor ever will be, obviously, but and then the last thing I want to say here is that Max Tegmark's view is the following: I think consciousness is the way information feels when it's being processed in certain complex ways. So there we are. That's my introduction.
Just to fill in for completeness, where were you born and grew up?
I learned nothing about Bob there.
There's nothing much to say. I was born. My father was a double E at Western Electric in Baltimore, which is where I was born, and he actually managed he was a very, very inventive person, a very brilliant guy, and he was managed the communications cable development for Bell for many years. And
your mother?
My mother was a stay-at-home mother. She was went to Goucher College, I believe, in Baltimore, and loved business and investing. And so, when she wasn't trying to deal with all my shenanigans, she was working on investing in the stock market and stuff like that. So I was a bundle of trouble, I'm afraid. So therefore, I like to just skip over that part of my life.
I see. And do you have a family currently? Any children?
Yes, I have a son who works about a mile from here. Actually, they've recently moved. He works at Google. And I have a brother who is living in Utah now. My brother was a double E, worked for Bell Labs in Boulder, Colorado.
Has your son paid you back for your troublemaking when you were younger?
He's such a great, fantastic kid. He didn't. He's a lot more level-headed and much more responsible than I ever was or will be. So, my investment in him was worth it.
Great.
Yeah.
Well, thank you very much.
Sure.
Anything else on your personal fronts that we missed, or?
You didn't say anything about your family, Tim.
Well, I don't really have any happy news. I'm sadly widowed, so my wife passed in 2009. So.
Sorry to hear that.
Thank you.
Okay, so let's turn to the meat of our interview. John, perhaps you could take over and give us the background and context that energized the rest of the team here.
Okay. Chris called me up, and in a moment of weakness, I agreed to do this. And then later on, I was trying to think of a good way to worm out of it, and my wife told me to man up. And
It's funny, I had exactly the same feeling. I can't do this. Too shy, too...
By the way, the person you could blame for this is Bob, because Bob, I went up and talked to Bob in Almaden, trying to poke around how this happened, right? And Jim by then had passed away, unfortunately, Jim Eaton. And first thing he said is, I've got to talk to you because you were a key mover behind this. Not only that, you funded the work, a lot of the work. So I said, I have to draft you. This thing wouldn't be complete.
thanks, Bob.
Without you being here. So that's how you got into this.
That's fine. Glad to be here. I'm here partly because I joined IBM also in 1978 and had a very unique career in that I was in tape development for 31 years. So I've only had one career, but it allows me to kind of provide gaps in the history of the business that I experienced. I joined IBM because it was I'd been moved and I wanted to get moved, and they hired me in Tucson, and I'm still in Tucson. So I was reflecting on our relationship as a developer with the research organization, which is in IBM, it's an autonomous organization. And when I joined IBM in '78, I was doing mathematical modeling of the head tape interface. And I was asked to come and give a presentation to the research community. I think I'd only been in the company for 2 months. I came out and there was this really intimidating hall in the old research building off Cottle Road, which you probably never heard of.
Oh, sir. Building 28.
Yeah, 28.
Oh, okay.
Yeah, the triangle. Yeah,
And,
that's
Gone
right.
now.
Yeah, right.
it was a horribly boring presentation. Even I thought it was boring. And it took an hour, and I was just scared to death because it was such an intimidating environment for me as a relatively new employee. But I ended up visiting research pretty much annually every year for one event or another, and experienced a number of changes in the various processes and voodoo models to establish research priorities. And the answer always seemed to be that most researchers worked on what they wanted to work on. True fact. And in some cases, research even competed with development. Think GPFS, for example. There were some research hatched things that development didn't adopt, and then research would champion them, and got some success with many of them. But in general, I was not aware of any actual tape activity in research from when I joined in '78 up until events around 1989 or 1990 that I'll discuss in a minute. So we'll just jump to that. I think it was sometime in 1989 I came to work one day, and there was a task force report on my desk that my boss had put there, written by a guy named Dr. James Eaton. I'd never heard of him. The subject was tape, and this was fascinating and exciting because I didn't know anybody else in IBM cared about tape. And so I read it with eagerly, and I think I kind of summarized it as a scaling exercise to look at the potential, upside technical potential in tape devices. And in particular, I recall that it centered on track density as a primary, highly leverageable concept. And I don't know when HDDs adopted track following servo. I didn't think it was till the 90s, but...
No, it was already in 89.
Oh, okay.
Yeah, but it was quite new at that time.
Okay, gotcha.
Yeah.
And so that was my takeaway. That would be a tremendous artifact if anybody has a copy of that report. I looked through my files and I didn't save one, unfortunately. Dr. James Eaton, I found out, was a luminary in the research community, had participated in lots of things. And we became very good friends over time, partly because he understood my world, and that's always comforting. We didn't know who commissioned, sponsored the report. We didn't know why. It just kind of came out of the blue. In hindsight, it became clear that IBM had been positioning the root technology of the tape drive and the hard disk drive, not the subsystems, not the robots, but just we'll call them the bricks, if you will, for exiting from IBM in some fashion. And there were weird organizations that got formed temporarily. We were split out from what was SSD, and there was something called the Storage Technology Division briefly. There was just hard disk people and tape drive people. I actually worked for a guy named Mike something, I forget his last name, in San Jose. He didn't even know who I was. The Storage Technology Division suffered from an unfortunate acronym that,
Yeah, that was always funny.
that a lot of people made fun of. And so I kind of after the fact put together the idea that part of the reasons you do that, by the way, is so that you can generate a set of books specific to what you want to get rid of.
Yeah, yeah.
And so that it can be valued appropriately. And there's, a number of ways to value a business. When I joined IBM, it was mostly an annuity stream company, but that's another subject. So it turns out this report apparently generated enough excitement that whoever was trying to exit our business decided to give us a shot at it. And it presumed track following servo. We had zero experience with that in Tucson. Number of work scopes became obvious. You've got to figure out how to generate a position error signal. You've got to enable the ability to actuate the head laterally, which was not done at the time, create a control system, etc. And we didn't have these skills, and we didn't even have any real knowledge of it. In 1989, when this report landed, we had just shipped the last of the 3480 compatible tape drives that dominated the 80s. We really didn't have any direction after that. Interestingly enough, I racked my brain for if this task force hadn't come along, what were we going to do? And I don't remember us having a plan, so this became the plan. And I agreed to fund directly some people. Jim had connections at I believe it was the Stanford School of Applied Physics or something like that, and identified Tom and Rob Barrett, Jackie Spong, among others, and formed a little working group that was really focused on tape. And I chose to fund it myself because I thought the jobs in research were more important than more jobs in Tucson. Most managers don't think like that, but it was absolutely the right decision. And it helped, it instills ownership, it instills commitment to the team goal. And as far as I know, that was kind of a unique structure in IBM. I've never known anybody else who enjoyed that close of a relationship. So it wasn't just them dreaming stuff up and we got to go figure out how to do it. They were figuring out how to do it and help us. In some cases, Tom will talk about something called Time-based Servo. Tom handed that to us on a platter. I remember the day that Jim and Tom visited my office in Tucson and showed it to me. We were walking down the spine to lunch, and I asked a question of Tom. I said, "Is this velocity independent?" "Yes, of course." I said, "Okay, you're in. We got it." It was I'll never forget the moment because that's when things really started to click between the groups. sent Jim Garp up to meet you and figure out how to put it in a chip. And I wandered there, but let's back up just a little bit. IBM shipped its first tape drive in 1952. I wasn't there. 89 was the last of the tape drives. During that span of time, the first tape drive had 7 tracks. The last tape drive had 36. So that is a half an order of magnitude in 37 years. I don't even think we could justify staying in business these days with that as our roadmap. And the capacity wasn't much better. I think it was 2 orders of magnitude in that same period of time. So I'm talking about tracks and track density. We didn't pay too much attention to it. It was more of a solved variable than it was a variable to be designed. And I say that because the first tape drives were a replacement for the punch card or key card or Hollerith card. There's a lot of names. They were based upon something called a character, which is derived from a typewriter keyboard. Characters were 6 bits plus parity, 7-track tape. Later on, when the first hard disk drive shipped from IBM, I believe in 1957, they had defined something called a byte, which was 8 bits plus parity. So tapes became 9-track tapes. And then later on, somewhat highly, the very first tapes, the first 7-track tapes, there was a 1-to-1 correspondence between the magnetic image on the tape and the character. You could actually put a iron solution on it and you could actually decode the tape just like you're reading a punch card. And over time, that 1-to-1 correspondence became completely gone. There were a number of evolutions in tape formatting, including CRCs, ECCs, compression, a whole bunch of them. And so by the time we shipped an 18-track tape, 18 was just totally random and awkward number. And I don't know why, because it didn't have a 9-track compatibility requirement. So I don't know who did that, but it wasn't me. And then 36 wasn't compatible with the 18, and it featured eliminating rewind, even though at the end of the day, nobody cared because nobody wrote a whole tape anyway. And so this renewed focus on track density now is a variable to be solved. We also felt at the time in '89 that we were kind of out of room on track density opportunity because of how we recorded the tape. The recording head spanned the entire width of the tape. There are environmental factors that cause that tape to become narrower or become wider, creating what we call track mix registration. And we felt kind of at the limit of what we could do with tracks. And it was the Eaton Task Force report that led us to the idea of what we call a banded servo, where you're not writing the whole width of tape, you're writing perhaps a quarter of the width, quarter of the width, quarter of the width, quarter of the width, which then just literally scales that error down quite a bit. So long story short, we got the relationship going with research. Some great things came from that. Initially, we didn't have a strong target, but we decided to target what was called open systems. At the time, all IBM tape drives only hooked to IBM mainframes, and that was it. It was SCON, FICON type of thing. However, there's a growth opportunity in tape in what they called the open systems market. There were a plethora of formats. Although IBM was a tape supplier, we were also a huge customer of all these open formats for our other servers besides our mainframe servers. So we purchased quick drives that Bob mentioned from Tandberg, quick media from 3M, and that was for the AS400 platform. We purchased 4mm DAT/DDS drives from Seagate, the media from Sony, So this was an adaptation of the Sony Philips digital audio tape, and that was for our Windels. We purchased 8mm helical scan tape from Exabyte, the media from Sony, and that was for our RISC platforms, RISC AIX. And the mainframe market was just growing with the industry, and there wasn't much growth opportunity. IBM was more interested in a growth business than an income model. I missed the dividends, they were pretty big. And Exabyte was king of the hill at the time. So we basically specifically targeted Exabyte for the first deployment of this new thing that we were developing. We came up with kind of a novel, cool little cartridge, and eventually shipped a drive that hunted down and killed Exabyte wherever it lived. Because a lot of where Exabyte lived, the night watchman punched a button when he went home, and in the morning the job was aborted. And Coyote was only sold in an enclosed black box automated, internally automated system, and it was just reliable as all get out. I got letters from customers just ranting about replacing Exabyte with Coyote and how much it improved their life. So that was a good thing. It wasn't long-lived. A couple of years later, there was a change of the guard. A lady named Barbara Grant became the big boss, and her first announcement was that tape is dead. And we're phasing out of the tape business. We had a small portion of the Coyote team that was working to leverage that technology back into the mainframe drives that was known as Magstar, or 3590. The Magstar tape people were told, stay, finish the product, and we'll get rid of you later. Very motivating, I'm sure. And that Coyote team was told, you're done, you're leaving, we just don't know how and we don't know when, but we'll let you know. There wasn't much else to do. We kept working because we're still on the payroll, there's nothing else to do. And the significance of this event about 1992 was that Tucson lost its ability entirely to do any tape head technology. Mm-hmm. We had a pilot line where we could model and tool up to give it to Nancy Jubb and her team to do manufacture. All of that thin film equipment I watched as it was loaded on trucks and sent to the used equipment market. Kind of a sad day. That whole team ended up disintegrating. Some of them retired. One of them died. Many of them went to STK. And we all had to do something different. So I mentioned all these other open system tape drives. They took us bleeding edge developers and we became qualifiers of these devices, which seems insulting at first. Okay, I'm high-end world leader and I'm testing a quick toy tape drive. Well, that was, turns out, that attitude didn't last long. We learned a lot from these people. A lot about cost, a lot about integration. It was one of the funnest jobs I ever had. Plus, when I was told I was on managed to partner, frankly, I was scared to death. I didn't know how I was going to support my family. I wasn't connected external to IBM. So this was an opportunity to meet every CEO and tape leader and company in the entire universe. So that really developed my networking and made me feel comfortable that when they do let me go, I'll know what to do. Fast forward 2 years, about 93 or 94, another new leader named Jim Vanderslice. Dr. Vanderslice had come from the IBM printing business. And the IBM printing business was running a version of what's known as the razor blade model, where like HP, they were selling printers and then making a lot of money on paper and stuff like that. Just like 3M and X-ray machines. They'd give a hospital an X-ray machine so that they could sell them
The films.
the films for huge profits. We didn't know how to enable this. We were told to get back to work. I kind of flailed around with how do we, you know, I had told them there's no way we're getting back into the technology business. I mean, we're done in Tucson. They said, well, you know, we need a tape head. And the only place to get a tape head was the HDD line in San Jose. I had no idea how to do it. Bob mentioned we contoured heads and we slotted them and did all kinds of things that were foreign to HDD. We'll let Bob tell more about the story of the heads later. But probably the most significant thing that happened was in about '97, we announced that we were going to do a joint project with HP and Segal called LTO, Linear Tape Open. The motivation for that was that Exabyte conquered the world, as I indicated. Coyote was hunting it. And then a company called, what were they called? They bought the deck storage business.
Quantum. Yeah.
Thank you. In the deck storage business, they bought it mainly for disk, but they found a tape drive in there that was a proprietary deck-only tape drive. Fairly simple design. Certainly not made for the environments that we were putting our drives into, the large automated environments, or more standalone devices. And they recognized what they had, and they put an open interface on it and went to compete with Exabyte and killed them. They went out of business. And they became the darlings of the universe. And some of the non-technical leaders that we get in business are always, how come we can't do that? How come you're so stupid? You know, it just never changes in that. So LTO was designed to go hunt DLT, which is digital linear tape. So we did linear tape open, meaning we're not going to be proprietary. The moral of that story is when you're trying to beat a entrenched monopolist, you do it with an open standard and invite a lot of participation to gang up. When you're trying to beat an open standard, you need to develop a better mousetrap. They just go back and forth like that historically. So we got lined up on this LTO thing. Some other innovations came about that Tom will talk about. Longitudinal position encoding turned out to be, don't know if you know this, but one of the most significant contributions to all of tape history. And I can tell you why in a few minutes. Tom also worked on this Coyote project that we shipped before we started the LTO project. We had defined, loosely speaking, if a tape cartridge has if a tape piece of removable media has a single spool of tape in it, we refer to that as a cartridge. If it has two spools of tape in it, we refer to that as a cassette. So think of audio cassettes, VCR cassettes, and but those cassettes have hubs that float. And so when you insert them into the drive, they align onto the fixed motors. Coyote did not have floating hubs. They were actually pinned in the cartridge. So the interface between the cartridge and the motors in the drive becomes highly non-trivial. And that led to the second most significant contribution in tape history. So now I'll explain those things. Tom was working on the, we called it, I think, the flex clutch, to try to solve this problem of mating a fixed reel cassette to a drive, to two motors. And one of the byproducts of doing that was that he designed it in a way that you could only apply torque to the reel in one direction. Remember, we had the teeth at an angle.
Sure.
Which meant that we wouldn't ever In tape drives, free body diagram, you're accelerating the tape, but you're maintaining a tension in the tape. So as you increase the torque on one reel, you have to decrease the torque on the other reel. It accelerates and keeps the tension. And if you keep accelerating faster, eventually the supply reel has to reverse torque and actually push tape out. And this is how all the tape drives worked. So you take a piece of tape that has gone through that type of process and you archive it for a while. It will stress relieve. There's a lot of winding stresses, hoop stresses and radial stresses and these things that are a whole study of their own. And they can create gaps in the pack. And then when that thing is subsequently mounted, it can create something called a Z-fold, where you have a hunk of tape turning within the reel, causes a Z-fold. You don't know it's there. It creates permanent errors, all because of torque reversal. So when we got rid of torque reversal, we solved that problem. And I remember I was really proud of it. I didn't do it, but I got to talk about it to the analysts once. And I said, well, I'm going to draw some free body diagrams. It's only going to hurt a little bit. But they got it. Now, the other one I mentioned was the longitudinal position encoding. So Z-folds were a fundamental permanent error scenario in tapes until Coyote. Never happened again. The other fundamental error in tapes that was something called a chopped block. So when we're writing a tape, typically the buffer runs out of data, the tape has to stop, wait for more data, and reposition. That repositioning is a blind apparatus. It's based on timings and assumptions about the radius ratios between the two reels, and it's not rocket science, but it's a blind operation. And if for some reason there's any slippage or the tolerancing was incorrect or environmental factors, you might start writing and cut off the last block that you wrote on the tape. You've created a permanent error condition that will be discovered in the future. You don't know you did it, so you can't tell the customer you did it. And that's what we call the worst sin in storage. It's the bartender overserved you and you can be liable for that. So at longitudinal position encoding, think of it as a mile marker along a highway. You see them every mile. And it basically allowed us to know where we were in the tape so that we don't have to reposition blindly anymore. We had a whole new lexicon in tape called if L pause valid, you may write. But if it's not, you can't write. And this all just occurred to me one day at an analyst meeting. I thought, Coyote has addressed, did we put L pause in Coyote first or LTO? I don't remember.
LTO, actually.
Okay.
Coyote didn't have it.
Between those two things,
Yeah.
so I must have been talking to LTO at the time.
Yeah.
That was just so profound to me. These were the only two bugaboos in tape since 1952. Bang, resolved. And we can confidently say today, and people know it, tape is one heck of a reliable place to put your data. It's not going away till the sun explodes. You might have trouble finding a device to read the tape. But that kind of brings us up to that precipice of LTO, which is the topic of our research contributions. Another major work scope was this lateral actuation of the head that I talked about. We didn't even know if track following would work in a tape drive. I mean, we're talking about micron level motions. There is a vertical tension component based upon the way we used to do the heads, where they're wrapped. For all we knew, we're just going to push the tape up and down with the head micron, and you're chasing your tail. So that's how much we didn't know what we didn't know. And these are the kind of the gotchas that blow up schedules and things like that. Tim was involved in the actuator. I had mentioned to you, Chris, one day that I had writer's block and I was going to go have a drink. wasn't writer's block, it was memory block. I got to the bar and realized I don't remember anything about the actuator. Nothing. I don't know who did it. I don't know where they came from. I mean, you would think I would know, but
It worked so
it's 'cause it
perfectly.
just
it never,
I knew the name
Never
Tim
was an
Chainer.
issue, huh?
I had
I
met
never
Tim.
worried about it. That's right.
I had met Tim Chainer. I visited him in Yorktown. You were working on sympathetic vibrations and disc arrays or something like that, as I recall. I didn't really know, wasn't really conscious of your involvement in actuator. I knew Dave Harper, of course, was involved, in Jim Eaton. But I just, you'll have to fill in all the blanks here, 'cause
Right.
I don't remember anything about
Well,
it.
the Flex actuator actually went to Jim Eaton and Jim Eaton's group, and then from Jim Eaton over to you. So
Right.
there was not until later a more direct link with Jim Overacker when you.
Oh, I remember him, yeah.
And we started working directly with Tucson, but it started off with working with Jim.
Another honorable mention that didn't make it into any product was the flipper bearing. I was fascinated with it.
Yeah, forgot about that.
It was a cool concept, and I remember I wrote a model of it, and it was really, really fun. It was a Jackie Spong
Yeah,
thing.
exactly.
I mentioned that I may have been a little bit hasty telling Jim and Tom that timing-based servos in, because I was looking for an alternative to that other thing we were doing that I won't talk about. May have been hasty because I had no idea what a gigantic headache to format it would become. Because it turns out the way Rob Barrett prototyped it was not considered to be a manufacturable process by our manufacturing team. And we ended up going outside the company. I think we got a little bit lucky there. Another story for another day. I think that pretty much sets the table. Last thing, of course, is where do we get ahead? They told me to go to San Jose and don't come back till I form a group. So I came to San Jose and posted a job for the manager, start with the manager. Several people would come and talk to me, but I didn't realize that in San Jose, unlike Tucson, nobody makes a career move without their four godmothers and godfathers telling them to do it. No, there was a lot more career management in the San Jose environment than the Tucson environment. And I wasn't getting anywhere. And Kevin Reardon came out, my boss, and said, "All right, who do you got for me to interview?" I go, "Nobody." So we went to Bob Scranton. Said, "Bob, we got this problem, we can't seem to staff this position in San Jose," and it didn't make any sense to staff it in Tucson, of course. Bob and Kevin dreamed up this idea of making it a notch on your belt opportunity. Guaranteed 1 year in, 1 year out. We only want the superstars, and we're going to feature this as something you'll be able to have in your resume that not many people have. Sure enough, it worked. Shalea Asami signed on as the first manager that I hired. I came back a year to the day later, and I hired Neil Robertson. Came back a year to the day later, hired Gary DeCad. These were all people with research backgrounds, so this is very much ties into the theme of this discussion. Came back a year later, and Gary DeCad said, "I like this job." Still there.
Still there.
But Cholet did some of the early recruiting, and really notable people. Of course, Bob was involved in the group, got roped in. Calvin was brought in, Peter Kepi. Jim Eaton eventually was in that group. Really a special group. They had their own camaraderie and their own, and I visited them a lot and enjoyed all the visits. And then after I left, my replacement, forgot, Colleen Sanchez. Mm-hmm. I don't even think she knows you guys exist.
Well, she's moved on too. So.
Yeah, that's true. That's all right. So that's the background and backstory and hopefully the context. So Tom will talk about his contribution to LTO, and then Tim, and then Bob will talk about the head.
I should say this thing about Colleen knowing do I exist. Well, I did report to her She was a VP, your replacement. And we were at a meeting one time. It was an executive summit with our major media supplier. Room full of, I don't know if you ever went to those. They were, anyway.
Oh, I know what you're talking about.
Yeah.
The ones Diane Hellman used to run.
Yeah.
They were called Tape Summits, yeah, they were a big deal.
Well, no, this was an external thing. This
Oh,
was run
okay.
by actually Fujifilm.
Oh,
but-
gotcha, yeah.
Yeah. And in a room, and I was there, I was maybe the only IBMer there. Room full of 300 people at least. And Colleen was giving a talk, and she said, now, and I only mention this because you brought it up, she says, now, and she did know I exist, now I want to bring attention to, we have a rock star among our midst. Would you please stand up, Bob? And I went, oh God, rock star. And I couldn't live it down for the rest of the conference.
Cut.
So if nothing else, I was a rock star for a day.
That's cool. Okay, I think I said
Okay.
most of it.
That's very good. Let's fill in the big blanks. Now, Tom, take it from here.
Sure. So mainly I'll talk about the topic of how the timing-based servo and the LPOS, the linear position encoding, came about. And right off the bat, I mean, one thing really striking in your comments was how easily this was accepted and adopted by the Tucson team. I was fairly new at IBM at that time. I'd only been there a year or two when that happened. And so I had no reason to be prejudiced in any particular way, but somehow I had already picked up from all the people around me that getting a technology from research into a project or into a product is a battle to be fought. You really had to, they don't want your stuff, and you have to force it on them. And that wasn't at all the way this was. This was just the complete opposite, and really changed my perspective about IBM. And in fact, I think back of it with some of the warmest fuzzies of all my warm fuzzies I can remember was the adoption of timing-based servo, both for 3570 and then later for LTO, where it was not just IBM, but it was 3 companies that just said, we want it. And
And the focus was on best practice or best design, merit, technical
right.
merit
It
was the
wasn't-
focus. It wasn't
some
on
kind
the
of
organization.
turf battle, which is what these things can often become. So anyway, that was neat. So where did this thing come from? One thing I want to clarify, the basic idea was not mine. It was Jim's. And when I joined the company in '89, one of the topics that came up for discussion occasionally was the fact that the type of servo that they were trying to use on tape, which in certain respects had copied some technology from disk, and I'll get a little more clear about that in a moment, wasn't translating so well to tape because there were some unique challenges in tape. And basically the thing that Jim would highlight a lot, and I don't know whether this was the main thing for you guys as well, but he talked all about micro-track profile changes, and the fact that the head could wear or the head could accumulate some debris, and it would change the spatial response of the head, and that would create a servo tracking error, among other things. And that could obviously limit how what your track pitch could be and so forth. So here was the basic problem that was being solved. If you look at the servo systems that were used in disk and still are today, they all rely on writing 2 tracks next to one another that have different properties. It can be different frequency, it can be whatever. You just need could be different phase. Rochester was promoting their special servo for disk drives. In any case, you make an A track and you make a B track. These days we do it in little bursts, but it's still the same concept. You've got something on the left and something on the right, and you want to put the head right down the middle, so you're looking for an equal response from the left and an equal response from the right, roughly. And if something changes the spatial response of the head, like for example, if the head yesterday had equal response on the left and right side, but today is favoring the right side a little bit, you'll servo to the wrong position, and that'll get into your track misregistration budget, and at the end of the day you can't write your tracks as close together as you had hoped. So Jim he talked about that a fair amount, that this was a big deal and thought to be the main problem to solve. I also understand the whole field formatting thing, which was also compatible with that idea of 2 tracks next to each other. They actually tried to do it in the drive, where in one pass you'd write track A and you'd come back and write track B, and I think you even did a C to try to make these things. So you can do all that. But as we're saying, if the head changes, and it doesn't have this problem in a disk drive, because in a disk drive it floats on a cushion of air, and contact between the head and the disk is rare. So there's nothing really there to be loading up the head with contaminants, although disk drive we do have that problem, but at a lower level, and there's nothing wearing off the head and changing its properties. But tape is just the opposite. You run in contact. You throw particles into the tape to give it the ability to clean off the head, and so significant wear of the head occurs over the life of the head. And not only are you just slowly wearing this thing away, but you're also occasionally depositing gunk on it that stays for a while and then eventually gets worn off by these wear particles. So there's a lot going on in the tape head interface that cause this interaction of this head you're trying to use to servo to not be constant, and that was felt to be a killer issue. So Jim had this basic idea of instead of writing two tracks next to one another, if you could write a single track that was wide that had transitions with different slopes. And then if you're at the top of the track, these two transitions are close together, and if you're at the bottom of the track, they're far apart. And by timing when these pulses occurred, you could tell, am I at the top or at the bottom of the track? And so the concept is very nice. It turns out it has all kinds of other interesting advantages that we did not anticipate right at the beginning, and we'll come back to that in just a moment. But bottom line is this is a fundamental change in how you generate the servo signal, or what they call the position error signal. Instead of using two tracks and trying to servo on the seam with a narrow head, with a wide head, you go to make a wide track which is continuously variable in its own right, and you sample it with a very narrow head. Now, no matter what happens to that head, if you goof it all up, you put gunk on it, you make the left side of the head different than the right side of the head, the worst that happens is you might be off by, say, a micron in those days, because the heads were only going to be a few microns wide when servoed in this particular way. So it really put an upper bound on how much error could be generated by screwing up the head. And but there's a great big problem with this, in that that track I just described, with some transitions, say, perpendicular and some sloped, or more generally just at two different slopes, you can't write that with a normal right head. Right heads don't do that. They make perpendicular transitions, or at least all parallel. And so this is a major problem. And but both Rob Barrett and I were intrigued with this enough. We thought, hey, this is really interesting. It's completely different. It looks like a wonderful challenge. Can we write this track? And you were talking about the fact that the head we eventually came up with couldn't be commercialized. I think you've momentarily forgotten what we started out with, which is far scarier. We had a rotating drum with a magnetic film on it, and we actually did lithography on this round drum. Made some little slots in it that made patterns, sort of like what we're going to need to do on the tape. And then this roller would roll right down the tape with a big magnetic field right next to it, and you'd write these patterns.
I do recall it was something kind of different.
Now, and I was smart enough not to work on the roller. Rob was hired after I was, and he started. Actually, really smart guy. Really like Rob, just a brilliant guy. And so he goes, okay, I'll do lithography on a cylindrical surface. So he bought a blue laser, and we did all these things, and he would sort of dunk the thing in photoresist, and he would expose it under computer control to make these little chevrons or diamonds or whatever we had on it. And we actually made a few of those, and they kind of sort of worked. But it was really not a good plan. It also would have prevented all the things like LPAs later, because if you make the tape with a roller, there's nothing going to change. That
That's
pattern
true.
will get written
Now that you
again
mention
and again and again. At first, though, we thought that was no problem.
Well, we
it's
wouldn't
fine,
even
just
imagine the need, right?
Yeah, exactly. But that's where we started. And probably at home, I actually still have one of those rollers somewhere. But Bob and Jim then figured out, well, no, it would be much better to do this with a head. And at that time, the concept of a flat head was not yet there. So we made contoured cylindrical heads, where it's a section of a cylinder. And even had the cross slots and all the things that tape heads had in those days to try to make sure you had good contact between the head and tape. And then we would do lithography on that curved surface. Now here we didn't need to resort to that blue laser and trying to write on a full cylinder. We were able to use a flat mask, and we did it on a Casper aligner, a really old piece of junk that we had picked up for $300 from a surplus place here in San Jose. And we had it in our own little room because this was so primitive, and such many messy stuff, we knew that the HDD head research line wouldn't let us anywhere near their stuff, so we actually had our own little lithography lab upstairs where we did this, and had our masks made, and did make a number of these heads. I definitely have some of those at home still. I was thinking as I was driving up here today, I should have dug some of that stuff out and brought it along just for fun. But so the very first heads for writing this pattern were done basically by Rob Barrett, making them in research. And those heads even made it to 3M for a while and were being used. It was clear that there was no way we could support the needs of the business, and indeed, a lot of effort went into bringing up external suppliers to do that, which was successful, and I think they're still doing it today.
And they were individually wired.
Well,
so we could take them apart and play with them.
Yes, yeah. That's another. I'm glad you reminded me about that. The first heads. Not the roller, but the big cylindrical head. That was a ferrite head with a big slot through it, through which we wrapped a few turns of wire wrap wire. So that was it, one common coil to write actually several different servo tracks for several servo bands, as John had explained. So we were also in that configuration forced to write exactly the same thing on all tracks simultaneously. And since we actually put 2 gaps on the head, it also still was not, well, I'll expand on that a little bit later, but it was still fairly limiting what we did. Eventually, when it went into the commercial production, they learned how to put separate coils on the heads, and that was very, very nice in terms of being able to encode slightly different information on the 3 or however many servo.
They wanted to be able to identify which band you were in.
Yep. And an LTO for a while, at least that was, one was a little ahead and one was a little behind, and there were various tricks for doing that. So anyway, this whole business of how do you create this special servo track was a big deal. And Rob Barrett was really the hero who made that happen the first time. It's the kind of crazy project I would say most mature researchers would run the other way from. But he was young and he was very capable, and got it done. So I took on the much safer job of building the decoder. So how do you?
But before you go
ahead.
So where did the final pattern end up? How did you what was the final solution for the?
So in the case of
maybe I'm jumping in too soon, but I just thought it'd be appropriate to close.
No, that's fine. In the case of 3570, we had the diamond pattern already, right?
Yeah.
Yep. We called it the diamond servo for a while.
I was clued by Dr. Kluge when he left the business. He gave me a name and a number and said, someday you're going to need this. And it's the company was called ARC in St. Paul, Minnesota. ARC was Advanced Research Corporation, generic. And he had been working on how to do this. Yeah. And he had the 5 different servo tracks, the wide ones, individually wired. And we outsourced the business to him, and he had a great business model. He wouldn't sell the heads to the media companies. He wanted them back. So he had a lease model.
I see.
And then he would recall them when he wanted to, either because they were returned or he just wanted to study how they held up over time. He was really a smart guy. His name was Matt Dugas.
Matt Dugas, yes. Yep.
A little bit talkative, almost more so than Bob, I think. But yes, he.
And
so
the transitions were at an angle to the.
They were at an
That's
angle.
correct, yeah.
To
So
the
we actually
tapes,
ended up having a diamond pattern that looked like this. Actually had several transitions on one side of the diamond and several transitions on the other.
And covered a fraction of the tape, and you repeated that pattern, or in bands.
Well, these servo tracks, there was maybe 5 of them across the width of the tape. Yeah. That's all written simultaneously in the factory at the pancake level with these heads from ARC. The data's in between those bands. So the head will shift from writing these 2 to writing these 2 to writing these 2 to writing these 2. And then you put the data in between them.
And that's how it stayed ever since?
Yes.
To this day.
Yeah, a little bit enhanced for LTO with this linear position encoding, which we'll come back to. But yeah, no, the basic concept stuck.
Interesting.
So
And I would say ARC deserves a lot of credit for the enablement.
We enjoyed that
huge.
project. That
Yeah.
was great to try to dream up all the things to optimize this and understand it.
And that relationship didn't end well, not with us. But the media companies hated being dependent upon a single source to do their whole business. And eventually they found alternatives to ARC. And then that led to a bad divorce at some point.
Yeah.
Between Matt and the media
various
companies, not
lawsuits
us.
and things going on,
Yes,
as I
yes.
recall. Yeah.
I was departed. I was deposition. I was depoed or whatever they call it.
Anyway, long after I left IBM too, I was helping patent
Were you?
attorneys fight about that.
And I thought, well, this will be easy. And I went in there, and the lawyer said, well, I'm going to train you on how to do this. I don't need training. I'm an experienced executive. I can handle myself. By the time he was done training me, I felt like the biggest idiot in the universe. These lawyers can just nail you to the wall. And to the extent that engineers like to talk,
Use it against you.
they use it against you.
Yeah.
And I said, well, he said, did you ever apologize to Matt Dugas for? I've never apologized to anyone. He shows me an email, John Teale to Matt Dugas. I'm sorry about it. Turns out it was a damn fake email that he had made up.
Wow, really?
Wow.
Oh.
But his point was, do I have your attention yet? Anyway,
Sorry for the distraction.
that's
I just
great.
wanted to capture that.
so we got closure there.
No, that's great. That's a fun aside, and by all means, jump in if at some point you've got an interesting tangent. I like to hear it too. so anyway, as I was mentioning, I kind of took on the job of making the servo decoder. So let's say Rob Barrett is successful. We have this tape formatter. These patterns are on the tape. Now we need some narrow head, and we have to read these transitions and turn that into a position error signal. It's not so hard. It's fairly straightforward logic, and you probably picked up a little bit in my background story. You know, I'm not really a trained electrical engineer. I went through physics and so forth, and a lot of my electronics was self-taught stuff I did as a hobbyist. So, but I felt it was really important for us to really demonstrate this and make it into a nice package that we could show to the Tucson folks, where it really did spit out the PES. So I built the first decoder using wire wrap and TTL chips, which was very much out of date by 1990 or 91, whatever this was. This was already a 15-year-old way of doing things. But I knew it, and I was familiar with it, so I put in 1 million wire wrap wires and made this big rack thing with a bunch of stuff, and it mostly worked. It wasn't perfect. We did implement a few other things along that come up. As soon as you start working with a pattern like this, you realize there's a bunch of stuff you can do. One of them is error checking. So you're basically timing various transitions, and we had several of them running in parallel, sort of nested intervals. And you could check out how these 3 or 4 or 5 intervals that you were timing, whether they agreed or not with each other. And if they didn't, you could flag this as a low confidence PES sample. So we had that built into this circuit as well. And of course, velocity sensitivity, we took that out as well. We had a special thing that would compare the time of this variable burst to one which was fixed, which was actually the distance to the next pair. And that one we could use for normalizing. If you were going slow, of course, all the bursts took longer, and you could check the timing of that fixed one to tell you how to adjust the shorter one. So bottom line is we put a few features in there for error checking and also for velocity cancellation, and made it all work. And I'm sure guys like Jim Karp were just smiling when they saw the way we did this.
But Jim is like a world expert at what he
Oh,
does.
fabulous guy. I respected him very greatly because he saw what we did and he goes, oh, that looks like a good idea. We should do that. But he did it right, of course. Programmable logic and things like field programmable gate arrays were just becoming commonly used at that time. So he turned around and took my giant box and compacted it down into 4 little chips that actually worked a lot better.
Yeah, he did the timing base. Jim also did the first Reed Solomon ECC and tape.
Yeah.
The first SCSI interface
I'm
and tape.
not surprised. Yeah.
Tremendous stuff that he
Yeah,
did.
just a really fabulous guy. So
He was smart, and he'd tell you.
Well, for whatever reason, I never picked that up from him too much, that there was an ego behind that.
Because you didn't live in the same town.
Exactly. We saw him only occasionally. For us, he was just really nice and very helpful, and obviously had skills that greatly enhanced what we were trying to deliver.
I want to do just a quick interjection here. Tom mentioned there were beneficial byproducts of this concept that certainly weren't by design at time zero. They were kind of, oh, we can do this, we can do this. One of the things that we were able to do was use this servo pattern to provide the velocity position error signal for the motors so that we could get the tacks off the motors, which are unreliable.
That's right.
And completely eliminated hardware cost, reliability issues, and in conjunction with LPOS, my interest in LPOS when I first asked you to consider it, and I think I had to ask you twice, and then the second time you did it, I wanted to get rid of the tacks altogether. But then I needed a way to know what are the radius comparisons. And so LPOS for me was a way to.
Exactly. Now I remember
in
that.
conjunction with the velocity feedback. Wow.
Yeah.
That's a robust.
And this was cool.
package.
We had put in the ability to measure the velocity simply because we wanted to make the position error signal velocity independent. I wasn't thinking about his problem at all.
Right. No, you weren't.
But we were spitting that
What's a
velocity out.
tachometer?
That data was there for free, and just the way
It
we
was.
built it, and it's sitting there spitting out the velocity on a continuous basis.
Serendipity is real.
Took him about, I think, probably a microsecond or something to figure out, oh, we can use that.
Yeah, yeah.
And
I had a
so-
lot of things going on in my head.
Yeah, yeah. And since you're mentioning other positive side effects, another one which we totally didn't understand when we started this project off is the fact that if you made this servo pattern in generation 1, you could leave it alone for generation 2 and generation 3 and generation 4. You did at least 4 generations, maybe more, because once you have this continuously variable pattern, unlike the case where you're trying to servo on a seam between 2 different tracks, you can choose anywhere you want to servo in that pattern. So if you want to double the track density, you now just have 16 defined points rather than 8 or 32. And that became another sort of unanticipated benefit as we ended up making something that was just wonderful for intergenerational scalability and also intergenerational compatibility to the extent you wanted forward and backward compatibility. The servo wasn't going to be your problem. What you did on the data tracks probably mattered quite a bit, but the servo would just plain work, whatever you wanted to do for many generations going forward.
I like the word robust. It was that's a powerful word.
Yeah, yeah.
And it was very robust.
And that error checking in there and the fact that it wasn't susceptible to headwear and all these things, that all kind of worked out. So yeah, and indeed I was quite surprised how quickly that was adopted and used for Coyote.
I think it took them 30 minutes.
Yeah, and I know
Sold.
that they had wanted it for 3590, but it was too late. They already
They
had
had
something else.
their own set of issues.
Yeah, exactly. But then fast forward a few years, LTO comes along, and this was just another wonderful example where something was adopted with no resistance. And the 3 companies, Seagate and HP and IBM, getting together to create this DLT killer. We all understood what we were trying to do.
Right.
And to a large extent, we tried to copy many things about DLT, same general cartridge size, same, well, no.
Yes.
In any case, but all 3 companies coming together, probably there were many things where technologies competed between the 3 companies. Somebody wanted maybe a certain tape formulation or a certain head technology. I don't really, you'll know far more of those things than I do. But at least my understanding was that everybody just said, no, we want IBM's timing-based tape servo. And in it went and became a very vital part of that and ended up generating really nice royalties for
Big
our company.
royalties. And the
Were
place
were you able to patent some of these
We did.
ideas?
We patented it pretty well, not perfectly, but pretty well. And so yeah, and that enabled these pretty bulletproof coverage that generated the royalties for many years.
still are today.
Still today. And it's how much in aggregate?
Well, it was running, when I left the business, it was running about 180 million from LTO alone a year, divided by 3. And that's revenue that doesn't cost us anything to generate.
Yeah, yeah.
That basically was my development budget. It's a free development. It's paid for.
Yeah.
And, but that didn't count the ones that we got from our individual suppliers, which were outside of the scope of LTO, where we were getting an additional 2 to 3%, depending on the product. Like, for example, the Jaguar version, the enterprise version of LTO that replaced 3590. That was a whole separate
Yeah.
annuity stream of royalties.
So this ended up being a rare case where IBM sort of properly took advantage of the IP it owned and actually got money out of the rest of the world for it. You know, IBM always had more patents than anybody else in the world and basically got very little for that over the years that I worked for IBM.
Well,
this
we
was
got
a
it done.
wonderful exception.
We got billions.
Yeah. So this was really cool to see these patents. And since you brought up the patent, I'll just 30 seconds on this. Rob Barrett and I were busy writing these patents. I think Jim was in there too, obviously. Jim and Rob and I, and maybe certainly in later ones, Tucson collaborators as well, like Jim Karp and later Glenn Jaquette when we get to LPAS. But at the beginning, it was just Jim and I and Rob writing these things, and they wouldn't give us the good patent attorney. If you remember, we had a really good patent attorney at Almaden. What's his name? Well, anyway, it just escapes me right now. I thought for sure I would remember this guy. Tom Berthold, that's the guy. You may remember that name.
Yeah, I remember Tom, yeah.
He was just wonderful to work with, but they only gave him HDD stuff because that was way more important. And so we got some hired hand, an external guy who really didn't know anything about magnetic recording at all. Just a horrible patent attorney. And in the end, somehow we felt this was an important patent, and Rob and I wrote that patent application ourselves. We had each done enough patents by that
The
time.
whole thing?
We kind of knew the
Even all the boilerplate.
yeah, all the boilerplate and all the funny language they use and the structure of the claims and all that. So actually that was in a way that I ended up having actually more than 100 patents with IBM, but those were the ones where I really had to step up and write the patent application myself because the person we were assigned to was so bad because they were considered, this was tape junk. And yet, probably no other Almaden patent made more money than that one, I suspect. So anyway, funny story on the side there.
We
Were you able to, sorry, I wanted to, don't forget to bootstrap us to longitudinal.
Yeah, no, that's the very next
position
topic
encoding.
I'll touch on here. Yeah.
You wanted to say something, John?
Oh, I was just going to say in tape we had a saying that if you talk to a Japanese person about their culture, they'll say China's the mother culture. We're the children of that. We used to say tape is the mother culture to disc. We did everything in tape first. I mean, a multi-track system is a RAID by definition. People in San Jose still don't admit this, but we did ship the first magnetoresistive read
That's true.
in
Absolutely
1984.
True. Yep. Way ahead. Yeah.
It was a center tapped shunt biased head. So a lot of people think, well, that's not a
Doesn't
real
count.
Well, it does.
It does, absolutely. Yeah. Yeah.
So I don't know why I said that. Just
Well,
tape junk.
There were good reasons too, because tape was at a low velocity, so MR paid off sooner for
Oh,
tape than
well, yeah,
than it
there's
did for-
the backstory on that is
Yeah.
that the DFEDT heads, we just had to keep moving the tape faster and faster and faster and faster to increase linear density. And it was ridiculous. I think we were doing 4 meters per second or something in 3420. And the magnetoresistive tape head was another one of those serendipitous. It solved that problem, and we didn't realize how many other problems it was going to solve down the road. And every bit as good a story as Time-based Servo. But
So in the case
Anyway.
of Servo, of course, disk did go first, but the cool thing
True.
is we didn't copy them. We actually did our
right, there we go.
So that was that. So then, yeah, the one other sort of big topic on the servo thing, but it won't take nearly that long to explain, is linear position encoding. And it became clear, and this was really a pull from the product people. We in research didn't really appreciate that it was very important. We thought, well, there's other ways to know where you are on the tape. Why can't you just write in the data tracks or something? I don't know. But in any case, you guys were quite clear after a while that no, we really would like to know where we are on the tape, and you should be able to put it into the servo. And of course that's true just by sort of putting in special little perturbations on the servo pattern, moving one transition a little ahead and the other one a little bit behind. We could in fact do that in a way that did not affect the position error signal, because we were timing several intervals per sample. So if we made a few of them longer and a few of them shorter, we could hide some additional information in there without screwing up the servo at all.
Unbelievably.
And that signal was also picked up by the same head that
Correct, the servo head.
the servo head,
read head.
not
the
a
same
separate head.
It's processing it differently.
And was able to be written with the servo write heads that were already in use at that time, just by changing the timing of various pulses slightly.
So the integral was the same.
Yep.
But inside it, you get the differentiation.
So we had a sum of A intervals that didn't change, and we had a sum of B intervals that didn't change, but the individual ones did. And that allowed us to stick a 1 or a 0 in each of these bursts going down the tape. And you don't need a lot of data. You know, the data rate here is abysmal. I don't know what it would be, maybe 100 bytes per minute or something. It's
it
not
was
quite
pretty
that bad.
small. It was pretty small.
But it's a small number like that. But that's enough.
But
to
you're
tell
not
you where
wasting
you
a
are.
lot of tape to wait for L positive value.
Yeah, exactly.
I mean, it's well worth it.
Yeah, and it allowed you to know much more precisely, because under that procedure that John described earlier, where he was worried about, truncating a block, you had to leave plenty of extra space to make sure that didn't happen very often. But if you know much more precisely where you are, you can bring these blocks closer together.
Yeah, radius ratios are very crude.
And I do want to give a lot of credit to Glenn Jaquette, Tucson, another guy, sort of another smart guy, just like Jim Karp, but a little different background. He was good at coding and channels and these kinds of things, and probably lots of other stuff too. Yeah. But I knew nothing about coding and channels, just because I was more thinking about other things. And so I knew how to put these 1s and 0s into the patterns, but I didn't know how to create a system out of that would really efficiently use this, and also do error checking and all the things that you want to do. And Glenn just took it upon himself to work with me, to teach me how the kind of coding that would be necessary for that type of serial bit stream would be done. And then once I kind of understood it, he and I sort of competed it with each other in a very friendly way. I'd send him an email one day, he'd send one back the next day, say, mine's better. So I'd send one back the next day, this is a little better yet. And finally, after a while, he stopped answering me. He said, this is good enough. So
at the asymptote, you stopped, right?
Yeah. And in any case, that became the linear position encoding system that was adopted by LTO. And I don't know whether that's been, greatly enhanced over the years or what. I didn't pay attention to that after that time.
Not to my knowledge.
It's still being used.
Glenn was a person that you had to have super clarity in what you wanted.
Yeah.
And minimum of constraints. Mm-hmm. Over-constraining engineers, really.
And I think this was perfect for him, because we had a totally
So I was good
clean
at posing
slate.
the problem.
Yeah.
I'd pose it. Glenn was more of an architect.
Yeah.
Where Jim was the hands-on nuts and bolts guy.
Yeah. But this worked out well. This was a clean slate, so between Glenn and myself, we could just do that LPOS
that was
and
cool.
decide what it was going to be.
And you didn't know what it was going to enable. You were involved in solving the 2 biggest problems in the history of data.
Yeah,
They're eliminated.
Didn't understand the significance of it, or maybe I would have been more intimidated or something. I don't know.
So now we know where we are on the tape, and we want to decide where we're going to go to, right? So how did we actuate the head? How did we marry the head to that signal, right? Mm-hmm.
Well, in a very quick nutshell, but obviously this is mainly Tim's bailiwick. It's take that PES signal, run it into the right compensator, and apply it to this actuator these guys made. And there's a lot of missing details there that Tim will fill in.
Servo control, digital servo control.
Please
So
pick up.
So the next
From
step,
here.
I guess, should we call it it was called the flexural actuator, or apparently the stealth actuator, because it kind of snuck in.
Yeah, I thought Santa's elves dropped it off.
So it's kind of back up, I came into tape from the disk drive side, right? We were not actually working on tape drives when we conceived of a flexural actuator. You got to go back into that time history. When I joined IBM in the 1980s, IBM was still making very large 14-inch disk drives, right? Very large disk drives. But the PC was just coming out, and the PC XT was the first to ship with a 5 1/4-inch form factor disk drive. I believe the first 5 1/4-inch disk drive came around 1980. And then IBM built its own 5 1/4-inch disk drive, which you might remember this name, Pixie, which went in the IBM PC AT. So there was this move to take these technology from this large enterprise system disk drives with all this advanced technology and start producing small form factor disk drives, in part driven by the PC. At that time, Dave Thompson, and I don't know who perhaps in Ahmedin, but what was started was the Compact Storage Lab. Maybe Chris, you remember how that was started. And the goal of that was to start looking at ways for IBM to build more small form factor disks. In fact, there was a company that came out with a 3 1/2-inch disk drive, which was Rodime, if you remember that name. So IBM wanted to start looking at smaller form factors. So I was working for Dave Thompson at that time, and we started working on 2 different kinds of disk drives. One was a small, very low form factor disk drive that was only going to be a 1/2 inch high. And it was going to be a 3 1/2-inch form factor. We had a second prototype we worked on, which might have been the first ever 2.5-inch disk drive. We built one with a 65 millimeter disk. But going back to the flat file, we decided that we would come up with a new form of actuator. And the nice thing about using flexures, which we invented in the early 80s, was that a flex actuator would have no bearings. So there would be no frictional forces. It could be made out of stamped sheet metal, right? So it could be made at very low cost. And those were the 2 goals of the Compact Storage Lab, right? We had to build small compact disks, and they had to be low cost if we were going to compete in this new world that we saw coming, which ultimately happened, right? 3 1/2 and 2 1/2-inch disk drives took over, and then RAID happened. And the large disk drives that IBM were making kind of went to the side. So there were a lot of challenges. And at that time, also to build compact storage, research wanted to up its game. We didn't just want to build a component, we wanted to demonstrate full functionality. So we built what was known as the flat file prototype, which was going to be a fully functional 3 1/2-inch disk drive, which we were going to server write and then demonstrate actual digital servo control, the seek performance, which is what you alluded to. How do you move from one track to another? You have to have a servo control and a position error signal, and you would close the loop on this actuator. And so the way the flex drive works is it's parallel motion of 2 springs, and it produces a parallel motion of the head. And we got quite a few people involved. We got Dana Brown from Rochester to come to research for an assignment, and he did the servo writing. And then Sri Jayunta was a servo control expert in IBM Research, and he closed the servo loop. We hired Wayne Sohn, who was a mechanical engineer, to further refine the flex actuator concept that many of us had invented, including Dave Thompson was on the patent, Suri Hegde, Bob Hammer, myself, and Sri. So it's interesting to see how the names change. We had the original invention, then we had the development of this disk drive, the flat file with another cast of characters, and then finally the third part of the project was to take that flexural actuator that we developed for a disk drive and to design it for tape drive. And so it had sort of a 3-step process, and the personnel along the way kept changing as we went from one mode to the next mode to the next mode. It turned out, though, just to go back to the flat file, that was going to be an amazing learning experience for everybody in the group, because that was the first time we ever server wrote a disk drive in research and actually tried to demonstrate real voice coil motor servo control. in my own case and several others, that was going to lead us to developing ways of writing servo patterns. And we ultimately came up with the idea that a disk drive should write its own servo pattern. We learned in doing servo writing that those systems were very expensive and required laser position systems to position the head to write these sequential servo tracks. And the interesting thing, kind of a side note, was that every time you double track density, you would have to double the number of servo writers you have in manufacturing. So we had an unsustainable model of manufacturing where ultimately servo writing was going to become the major capital cost of building a disk drive. And we know how, track density was going to scale thousands of times. So imagine, many, many orders of magnitude servo writers. So the ability for a disk drive to servo write itself became a really compelling technology, and we developed that in research and transferred that. In fact, the microdrive that you referred to was self-servo written in Fujisawa.
So does that almost eliminate repeatable runout? Because it's...
Yeah, it's kind of interesting because you're actually, it's a fascinating technology because it's kind of a step and repeat. You would write a track, servo to the edge of a track, and write another track. And you would do that, about 1 million times or so across the surface of the disk. Now, you know that if you have an error on any step, that error is going to grow with square root of n times the number of errors. So we had this built-in writing a track and measuring the error and doing that correction on the next thing. The thing that it actually did lead to, which was, again, serendipity, unanticipated, was that when you wrote servo tracks, your ruler really was the head width. Now it turned out as track density was scaling, head width tolerances were not scaling well with track density. And when we had finally left the business, it was something like plus or minus almost 40% of the track thing. So it came to our conclusion that self-servo write wasn't only a good way to write servo tracks, it was the way you wanted to write tracks. If you had a narrow head, you really wanted to have constant gap between the tracks, right? You didn't want to write tracks on a fixed pitch. You wanted to write a track, have a gap, and then write another track. You did not want to write tracks at the same pitch and have this plus or minus 30% error. And self-servo write gave you that naturally, and that became known as adaptive track pitch. Each disk could be written to the head tolerant to that head dimension on that particular surface, because then we were in sector servo and every surface had its own servo. So you're able to do that. So it's amazing how things spun from this effort of going through the process of building an actual disk drive with a servo pattern and then doing the servo control led us to this then next project, which actually went on for a decade and had been very successful.
If I could just take you aside for a moment, that may have been a first in the industry, the self-servo write approach, and then IBM adopted it.
Right.
And then has the industry, I think the industry then adopted it, right?
Yeah, when IBM divested and we went, all our technology went to Hitachi, right, HGST, self-servo write went with it. And now HGST merged with Western Digital, but I think they still maintain their name. But the last time I spoke to the folks like in Hitachi, there were hundreds of thousands of these self-servo writers, which are basically just electronic boards that are able to have each disk drive write itself. And the cost, it could be made arbitrarily small because it was just purely electronics, right? And you could
and I was curious because I didn't follow it. I assumed it would have flown through those sales, right? HGST, right. Then Western Digital, but did it flow to Toshiba? Did it flow to Segal? Do you know, or perhaps you didn't follow it after that?
Yeah, I know that it stayed in Hitachi. I don't know that it flowed into other into Segal.
Because it would have been an issue for them too, right?
Right.
I mean, this wasn't just an IBM issue.
Right.
What you do with servo writers?
Right. Everyone had to basically solve that problem, the scaling problem of servo writers. And I don't know what technology Seagate does. They may or may not have adopted things. There was another version called servo copy where you would put 10 or 12 disks in a pack. You would write an initial pattern and then you would populate the drives with these things and then generate a second servo pattern from the first one. But in self-servo write, you didn't need to do that. And that project was done with Ed Yarmchuk and Mark Schultz and K.F. Etzold and Buck Webb, and we had a group in research that worked for probably a decade to get that in. But now circling back to the Flex actuator, So we had this fully functional actuator, and one day we were contacted by Jim Eaton, who had this new tape program and was looking for a candidate actuator. And I suspect that Dave Thompson and perhaps even yourself had some hand in that link. I don't think Jim just contacted us outright, or somehow Jim was aware of the work of the Flex actuator through the, we had these regular meetings in Almaden, and we publicized all this.
To give you a background, before Jim started this tape group in Almaden, Jim also had a stint as, I think he was a third director of the Magnetic Recording Institute.
Okay.
He headed that joint, General Products Division research lab. And through that job, I think he got visibility to everything that was going on in research, including the compact storage lab. So I wouldn't be surprised if Jim took the initiative just on his own volition, right?
I would sure think so, that's how it happened.
I suspect nobody had to ask Jim to go look you up. He probably knew of your work.
He knew of this.
And,
one little quick question though, was the Flex actuator ever used in a disk drive?
No.
So actually tape is what ended up commercializing that. Okay, yeah.
And there were some reasons for that. One disadvantage of the Flex actuator would be that if you were in the off position, it would take constant power to keep it there. So it became somewhat power intensive.
Power issue,
right?
yeah.
Where in a tape drive, the stroke length was reduced by about an order of magnitude. We were plus or minus 10 millimeters on a disk, and it went to plus or minus like 1.75 millimeters. Now, having said that, it also got smaller. So if you look at a Flex actuator, you have to worry about a lot of things, how much stress you're generating in the bending moments. The way we did it, we made the ends bending, and we made the solid section rigid. So it bent as a 4-bar, almost like literally if you had 4 ball bearings and you had a 4-bar actuator. All the bending was occurring in these small sections. And it turns out that the stress depends on the ratio of those sections to the length of the stiff area. And then you have to worry about the force constant. There would be then the fundamental frequencies that would limit the servo bandwidth. You could have standing waves in the spring system itself, and then you could have torsional modes, right, out of plane modes. So one good thing in when we did the development, and Jim contacted us, we had developed a complete analytic model to the Flex actuator when we brought on Wayne Sohn. We have physicists, we tend to make things in prototype, and then you bring a professional mechanical engineer in there to remind you of the beam theory, and it really came down to finalizing. So we came up with a nice analytical set of equations, and when Jim wanted to redesign everything then to fit inside a tape drive, we were able to use that formalism to redesign it. For example, we had the voice coil motor outboard of the Flexes. Jim wanted the voice coil motor inboard of the Flexes. The length would change by about a factor of 4, the stroke almost by a factor of 10. There were going to be a lot of significant changes. So we were probably the perfect group in research for Jim to find. It reminds me of, if you remember, Ralph Gomery, when he was the head of research. He said, the perfect research project is one, by the time I hear about it, is already complete and needs no funding. So when Jim contacted us, he had a completely developed project, which he never had to fund us. It was free. And then he got us to build him prototypes. So in 1988, we delivered Jim the first prototype of a Flex actuator, and then we built 3 or 4 more. And that's how it basically the project got going.
One quick question, because I'm just curious about this. As I looked at that design, it had, and also your description you gave right now, there's a lot of overlap with the same problem space as HDD head suspensions. But from what I'm hearing, there probably was no connection between head suspension people and what you did.
Well, it's true. The head suspension people were building out stamped pieces of sheet metal, right, to create vertical compliance and stiffness in all these directions.
And worried about all the flexural
Right,
modes.
all those flexures. Ultimately, Tucson did get these manufactured somewhere. I don't know if they went to the head suspension folks to manufacture them or not. I don't know, John, do you know?
I don't have any idea. It's just a total blank.
But it was similar.
I'm sure I was involved.
Hutchinson Technology became the dominant suspension
Well, next door
maker.
had an actuator, and I don't know where that came from, and I don't know if it was the same as what you're describing or not.
So yeah, it's possible. It was the same type of technology. In fact, you could almost take like two head suspensions and put them in parallel and make a flex actuator.
That was a fairly much larger mass, as I recall.
Yeah. And then there's a voice coil inside that had to support that mass. So basically then that was the timeline. Then what happened is, after working with Jim on the prototypes, then eventually Tucson began to do development on the flex actuator themselves, and Jim Overacker was the person that we mostly interacted with. And he started redesigning it again. So it went from the prototype stage to a variety of different designs, but ultimately Jim was aware of exactly how it had to fit inside the Magstar, right? So it went through multiple designs, and then through that all we, emails going back and forth asking, well, could we do this? Could we do this?
And on the Coyote side, I think it was, you must have worked with Dave, I said his name earlier, Dave Harper?
Yeah, Harper.
Because he was the actuator guy, but he was in San Jose. Okay. So I didn't have a lot of visibility to his
Yeah,
work.
he came well after Coyote, though.
Oh, did he? Okay.
Yeah.
Okay. So at that point, I think the end result was we got the lowest resonance up to about 1.8 kilohertz. And one innovation that Tucson came up with was to put damping material on the flexures, because you had these standing waves. And your development folks, Jim Overacker, they came up with a damper, and that was able to reduce that mode, and they could get a higher servo bandwidth.
Oh, but the pay rate.
Right. And then it was a surprise that that actuator continues to be used over 8 generations of LTO products. They ended up with a dual actuator. They had a stepper motor stage to position it, and then they used the flex as fine control. And so it's evolved over the time, but still the basic flex went in and continued to be used. So,
was this the first application in a product of a flexure-based actuator? Or how did DLT solve that problem?
They didn't have direct following servo.
Yeah, eventually they did. After LTO, but I don't know what they did for an actuator.
Yeah, I don't know.
I was just curious if this is. And were you able to also get some decent patents out of this work?
Sadly, back then, no. IBM Research had a different bar level for patenting things at the time, so it ended up that we got a technical disclosure bulletin, if you remember at the time,
Yep.
Oh, yeah.
which gave us freedom of action to do that. So we weren't actually able to patent it, and there was a lot of prior art on flexures in general, and dealing with the patent attorneys, they globalize everything. So yeah, we were not really able to.
I have a footnote on that for you. I mentioned that it was a real eye-opener working with all of these companies that were making the open systems devices. Tandberg Data was an amazing company. Historically, they were audio tape. But they released a track following servo quick tape drive same year we released Magstar. So it's not like we beat them to market. And I had gotten to know these guys pretty well because I was qualifying their product. I visited Norway many times. Just clever guys. I mean, teams 1/10 the size of an IBM team.
Yeah, I went there once also.
Oh, good.
On one of those trips.
One idea they gave me was, I said, well, what do you use for your microchip for your controller? They said, well, you embed the PowerPC. You embed the whole core. Talk about taking cost out. That was unbelievable. And so we learned that from them, and then we did it. But I had to go there once to negotiate something called a sliver patent. Okay. There was some claim in their actuator design that our lawyers thought we were in it is. So I went with some lawyers because they were just leveraging my relationship. Right. Frankly, it was a bit of a holdup. I mean, I'm your biggest customer. Okay. Give me that damn.
Give me that.
So there was something there that Tandberg had contributed as well, but I don't remember specifically what it was.
How was it received by the LTO consortium, the other companies? I mean, the Flexure-based actuator?
That
Was there any pushback from them, or?
No, let me explain. We go into this ad nauseum in the LTO version of the oil history. That was about creating an interchange standard. Zero about any implementation. The only time we ever talked about implementation is if one of the companies says, I don't get it. I don't see how to do it. And if you really felt strongly that this needed to be part of the interchange standard, then under very strict guidelines, we could share an implementation to show the proof of the concept so that they could participate. But that's a big misnomer. There's a lot of people, there was nothing about product development that was part of LTO. It was an ad hoc interchange standard, if you will.
Thanks for clarifying that.
And in fact, you only talk about how to write the tape. You don't talk about how to read it.
Yeah, when we did the
Interestingly
LTO
enough.
timing-based servo, it was just all about specifying the pattern,
Right.
nothing about the rest.
It didn't tell you how to write it.
Yep.
And Tim, how long did your group stay connected with that work with Tucson?
Well, the first, so it started, again, in 1988 was the first time we shipped a prototype to Jim Eaton. In 1991, then we were working with Jim Overacker, and the MagStar product came out in 1995. So it was over that span of 7
About
years.
seven
Yeah.
years.
Right, from the conception. But of course, the flex actuator was actually invented probably back around 1983. The concept, again, not knowing it would end up in a tape drive, but it was a fantastic application. And again, driven by Jim Eaton's knowledge of everything that was going on in research and deciding, he was a genius level guy, deciding, what technology would fit to solve this problem, to have actual, track following servo on a tape drive. You needed a great servo pattern, you needed an actuator, digital servo control.
All came together.
Talented team.
I'd
of,
say Jim was
people.
kind of the glue there.
Yeah, it was an amazing glue.
So I gather, Bob, that the early tape drives that adopted some of these innovations were still based on ferrite heads,
Well,
right?
So this so-called flat profile HDD compatible process head came the first with LTO. That was the first product. So there are two aspects, I think, to the head, and I've been involved on both of them. I'm actually still employed at IBM, still working in the head area. Well, for the head area, I guess. So it's been since about 1996, I believe. So it's been a long career there. I didn't really expect to be doing that for as long as I have been, but it's been good. And there's always, when I'm working, there's always just one more problem or one more idea I want to get going on, and then they never end. I mean, and that's pretty much the way it is even today. But so in contrast with the heads that were being built in San Jose for, the last set of products was MagStar. These were heads built on nickel zinc magnetic ferrite wafers. They did adopt, those heads did adopt some of the thin films that were laminated nickel iron, nitrogenated nickel iron thin films, which came a little later. But the wafers and the fabrication of the wafers was unique and not shared by HDD in any other way. And so the initiative was, is there a way that we could just transfer everything over to using exclusively hard disk drive facilities? And I think one of the breakthroughs was that for this quick program that I mentioned, I think we learned that yes, indeed, it's going to be possible to. There's really no reason not to dream about building multi-channel tape heads in the HDD lines in San Jose. And something I didn't mention is that back in this group, this development group in San Jose in the early 90s that was headed up by Larry Spector, we actually explored different materials for the experimental heads that we were building. And in fact, we looked at this ALTIC material. ALTIC stands for aluminum oxide titanium carbide, which is a mixture of those two materials and hipped to form a very hard substrate that are used for the HDD wafers. For the main purpose that it's a hard and nicely machinable material. But in any case, we had some inkling back in, say, 92 or thereabouts, that wafer material would be a good choice for building tape heads because of its fact that it's very hard and not going to be worn out by the tape. In the course of the work that we did for the quick drives that I mentioned with Herald Datanetics, there was some work that I did on trying to, basically we were wondering, you know, how do we contour these single track tape heads for the quick market? This is a question that HDL had. So we were able to, as I mentioned before, we were able to produce wafers that had MR heads, which they wanted. They were on this ALTIC material. They had ALTIC closure pieces on them. And so the question was, you know, what are the dimensions, what radius, and what width, and stuff like that. And so I got engrossed in that problem to try to sort things out. And in the course of that, discovered that, well, you know, you can take let's call it a rail, and put a cylindrical contour on it, and you could, in principle, have the tape wrapping around the edges of the cylinder. And in that situation, we learned that wrapping the edges around the tape around the edges causes an air skiving to occur, and it causes a vacuum essentially to form between the tape and the head, the cylindrical part of the head. And what that vacuum does is it pushes the tape against the head to create a fairly consistent head-tape interface. So
Kind of like a Joe Block effect.
yeah, pretty much like that. And so then, you know, as we thought about it more, I thought, well, for the actual radius of curvature, you know, I mean, those heads were fairly narrow and had pretty tight radii of curvatures. But in the modeling that I was doing and in the thinking about it, you kind of reach the conclusion that, well, maybe a very large radius of curvature would work. And what's a very large radius of curvature but a flat profile? And why wouldn't that work? Now, I had a discussion with Jim, and I was trying to remember when, and I really don't remember when it was. It was before we hired him back to help me with this stuff. But he had mentioned to me that he had an idea for taking hard disk drive row bars, and to, you know, you have, say, 60 heads on a row bar, 60 hard disk heads on a row bar, and you want to, before you go to the trouble of fabricating them into sliders, you want to know, are they any good? Are they magnetically okay? So his idea was that, gee, maybe you could just take a magnetic tape with some signals on it and run it over these row bars and get a signal out. Of course, you'd have to make the connection to them and all that stuff. But anyway, it was a discussion we had, and I thought, and at the time I thought, that actually, you think that would work? And he said, oh yeah, it'll work. And but I didn't pursue it with him. But so there were these various thoughts that were on the table, and so that you know, so the one piece is that, can you build the wafers? And I think the answer to that was yes. And the other piece is that, can you fab the wafers? And we knew from the quick work that we could do that. Can you fab them flat? And if you can, then you can use the hard disk drive machinery to do that and cut cost. And we were pretty sure we could do that. And then, can you make a reliable head-tape interface from that whole entire methodology? So that's really the thing that we studied for the better part of a year. And
if I could just interrupt you for
Sure.
a second. It's obvious to all of you, but to the listener to this
Yeah.
of this history, is it, I think it's worth clarifying that I think until then, all, if not most, tape heads had a cylindrical contour, right? To allow for good compliance, right, between the head and the tape. And so the whole world of the tape world, right, grew up believing that that was essential, right?
That was the paradigm.
And you decided, well, maybe we could break it.
Right. So the idea of, the motivation was to leverage what was available in the disk business. And
Well, so to be clear, there's an air bearing, a hydrodynamic air bearing. There's a resistance of the tape head spacing, and tape heads were historically contoured, typically in a cylinder, to get a vertical tension component. And you can increase the tension to help control the spacing. The flathead is completely different and very, because it's basically atmospheric pressure that's holding the, because you're taking all the air molecules out.
Only the pressure.
So a flathead with a sharp corner, and it just like you said, skies the air molecules out, and which also helps with minimize head wear. Number of benefits.
Yeah, a number.
And it was a critical invention.
But it was anathema to the experienced head tape designers, right? A flathead. It must have been considered revolutionary.
We never really
right?
considered it seriously. It wasn't until we were making the LTO head that.
Did you realize you were stepping into this?
We were pretty aware of that, yeah. So the conventional wisdom, as John was saying, is you wrap tape around a cylinder for compliance. The tension, there's a T/RW term that pushes the tape against the head, and that controls the head tape interface. When you take away the curvature, how do you get the tape to conform to the flat surface? And the way you do it is you wrap the tape around the edges. If you wrap the tape around the edges, you skyvolve air and create the vacuum, which then causes the atmospheric pressure to push the tape against the head. The interesting thing is that there's an in-between situation where you can take the flat head and give it some curvature, but have it operate the same way. Giving it a little bit of curvature creates that extra T/RW term. Conversely, if you want to think about the older Blythe cylindrical heads, they didn't rely only on the curvature to keep to form the interface. There were also some air bleed slots that assisted that. So the thing that was really unique about the flatheads is that it just took away that T/RW term and just said, okay, we'll just rely on the atmospheric pressure pushing the tape down against the head. And that was the thing that we had to learn about and explore and make sure that it was going to work. Nobody was doing it. There was a paper by Hans Hinterrigger that I was aware of in '96, where he and another guy, another physicist, had done some studies of that particular situation. Anyway, we embarked on that by starting with row bars that we got from the HDD folks. And there were some rather shocking and unnerving things that we discovered kind of early on. So one of them was that heads wouldn't survive very long without in the form of a row bar. So in a row bar, you've got a substrate, and then the elements are in thin films at the other end at one end of the row bar, and then of course you have the skiving edge at the other end. You run tape over this structure, and you cause the tape to wrap the head, create this vacuum, and then the tape exits the side where the elements are. We found that if you had just even the slightest bit of wrap angle of where the tape is exiting over the sensitive elements, and turn the tape around and run it the other way, heads stop working in a hurry, in a heartbeat. And it wasn't really clear exactly what that was all about, but part of it was just wear that occurs, but there was some tribology taking place that seemed to be causing heads to become destroyed basically by, let's say, ESD types of processes that we didn't really understand. So it wasn't clear that, gee, if we put a closure on this thing, are we really going to be okay? Is there something strange about this flathead profile that's causing that? So that was an uncertainty. Another thing that we discovered was that when the tape is running over a cylindrical surface, the cylinder tends to put stresses in the tape that cause it to become flat in this direction. So when you don't have a cylinder, you can have what prevents the tape from doing that. And what's the problem with that? Well, if the tape isn't lying flat everywhere, and maybe it doesn't at the edges, then that says that if there are magnetic recording elements in this part that we want to have access to, we're going to have a problem. And it turned out that was Jim had attributed that phenomenon to anticlastic bending at the edges. And it actually turns out that some 3D modeling that I did showed that indeed it is expected, and it is in the elastic properties of the tape. The problem is that it was a fairly large effect, and so it had a pretty significant some constraint on how we designed those heads. So the way to circumvent that or to minimize it was that we had to make the heads narrow, and we had to increase the wrap angles by more than perhaps we were thinking originally. But all of those studies led to something that appeared to be viable from an implementation point of view. And so I think, John, when you came up and discussed, do we have a head for LTO that's going to be more amenable to put into practice than the current ferrite heads, which were much larger and had their sets of concerns and issues, we said yes. And I remember having discussions with you about this technology, which was in its infancy in '97 when LTO kind of came into being. So we were taking a gamble there. We had to figure out really how to reduce the whole entire thing to practice. How do we take the HDD process and in the most compatible way we can think of, get these closure pieces on there. When we have closure pieces on the wafers, how do we lap them? How do we make connections to the electrical contacts so that we can do the lapping? And just a whole raft of issues like that were really interesting and fun to resolve. We went from kind of an idea that it's going to work in '97 to a head that went out the door in the year 2000. So in 3 years we did it. Now there was a lot of work, and there were a lot of people involved in that implementation. I think that it worked out very, very well from a head tape interface viewpoint, and in fact, some of the serendipity. One of the pieces of serendipity is that as John was saying, that having atmospheric pressure being the mechanism whereby the tape contacts the head, it's very consistent as long as you're at, let's say sea level or not too high in the mountains or something like that. kind of kid. Yeah. And that led to studies of tribology where we were concerned about tape wearing heads out. Tape is abrasive and it can grind away at the materials in the recording gap. So I think having a more consistent interface there led us to have a better control over head tape spacing and all of the other tribology that goes along with it. And it's kind of funny, I remember a meeting that we had with Tanberg, who came to visit at one point. I don't remember. I think they were looking for some possibility of an alliance of some sort. I don't remember the details anymore. But anyway, we described what we were doing with them. And they came out and said that they were very thankful that IBM did that flathead, because they thought it was going to work, but they were too constrained by other concerns to actually try it themselves. But here we had done it and demonstrated that it was indeed viable. There are a lot of other things, other details I could talk about. They are mostly pertaining to implementation and performance. And
I'll mention one I'd like you to talk about, Bob. Tom earlier mentioned that the disk head is rarely in physical contact with the disk. In tape, basically your HTI spacing is the roughness of the tape, period. And that first LTO head, we had a lot of problems that came up that we couldn't anticipate. Some of them seemed to defy physics, black holes, weird stuff. And one of your major contributions was the tantalum shunt.
yeah.
If you want to talk about what that problem was.
Okay, so along the lines of what John is talking about there, and you had said, what patents do we have? So over the years, we've had to troubleshoot a lot of various issues with tape heads, and those have led to some pretty interesting, I think, conclusions. But the one of the things that we were dealing with is that there was this peculiar phenomenon of tape running over heads that we observed, where let's see, how do I put this in non-complicated terms? That if you connect a head, one of the tracks on a head to an oscilloscope, which of course we did, and you run tape, and you are looking at a recorded signal, you will see a sine wave or whatever the signal happens to look like. And then we noticed that interspersed with that early on, that there could be very large pulses that are being injected somehow, some way. And that was a very troubling thing. And actually it affected not just flatheads, but it also seemed to have an effect on some of the Magstar heads. We observed that. I think that's what you were referring to.
Yeah, I just remember the tantalum shunt was something you put in to,
right.
I think, control. I think some of the problems were asperities hitting the MR element. There's a heat transfer, and you did that too.
Were these thermal asperities?
So there are thermal asperities.
Yeah.
They're not particularly an issue. But what we were talking about here, John, that goes back so long ago, and I completely, I got to think. Okay, all right, now let's see.
It was one of the first problems we solved.
Right. Yeah. Well, one of a slew.
Yeah.
Okay. So let me go into that. So what that was due to, it turns out, is that when the tape is running over the heads, with the introduction of Magstar and then subsequently LTO, we have magnetic shields in the heads flanking the magnetoresistive sensors. First AMR, then GMR, and later TMR. But what we discovered is that those are just pieces of metal, pieces of permalloy, that are sitting in a sea of alumina, a few tenths of a micron away from the sensor itself. Running the tape over the head could cause those shields to acquire a charge, a tribocharge. And that in and of itself wasn't really particularly an issue. That I don't think there was any there would be no ESD breakdown or anything like that. But the really interesting thing is that the tape has conductive stuff in it. There's the back coat, which contains carbon particles, and there can be other materials that have some level of conductivity. When those asperities drag across the head and shunt this charged up shield with a magnetoresistive sensor, you could start getting phenomena.
Charge transfer, which would manifest itself in the signal.
It did. And it was a little bit. There was a little more complication to it than that. But the solution to that particular problem was to not allow these magnetic shields to be floating. And that was something that didn't bother only us. It was sort of an industry problem, I think, as it turns out, that we learned in hindsight. But anyway. So the shunt that John is talking about is we figured out a way to modify the head build process to include this resistive shunt between the shield and basically the substrate ground. And what that did was a high resistance path that led charge off from the shield, so they never charged up. And I remember, working on this. I had tried a bunch of different experiments, not, before I really understood what was going on there. And the interesting thing to me was that we built a wafer where, in order to test this idea out, we have a 36 track head. So we shunted every other channel in the head, ran tape on it, and then we look for noise. And we expect to see noise on the non-shunted channels, perhaps, maybe, but no noise ever on the shunted channels. And it was not a shades of gray, it's one or the other. And I remember walking out with some folks who were actually doing the testing on the heads that were built this way, and having a discussion with them. Well, how's the test look? And they said, well, it looks pretty good. The heads the tracks that have the shunt don't seem to have as much noise. And I said, well, no, that's not what we're looking for. I said, if there's any noise, the theory doesn't work. There's something wrong with the theory, or you didn't build them right. And they said, well, that's the way it is. And I said, would you please go back and look at the data? And okay, they'll go back and look at the data. I went to lunch, I came back, and one of the guys, just by coincidence, happened to be, I bumped into him outside as I was coming back from lunch, and came running after me and said, you're right. All of the tracks that are shunted are noise free, and all the tracks, Anyway, that was not much of a story.
You breathed a sigh of relief.
Right. It was that was a bad lunch with a good dessert. So Jim and I worked together on aspects of this, including designing the wafer and the closures and the lapping processes. Jim left and went to a group that you had formed per some initiation from you, John, in research. Yeah, and I think I was actually planning to come up and join you guys, and just couldn't get away from, dealing with all of the implementation issues that were lingering on, and then that turned into the next generation product, and here I am still there today. I don't know. So I think the story that's the story, and maybe it's hard to really communicate the breakthrough nature of this flat profile. But anyway, I think that's what I can say about that.
It was the big enabler. There's no way HDD was going to individually contour a lap at the head level. Yeah. That was not going to happen. We also at the time had a strong desire, or I did, to go into the OEM tape business. So I'd actually been selling our capabilities to Tandberg, to even DLT when they were still at DEC.
Oh, no kidding.
I visited them, and so I knew what DLT was. I just didn't know what it was going to become. Yeah. And unfortunately, the flathead, while it solved a lot of problems for us, it caused problems for potential OEMs.
Yeah.
Because they were still on that paradigm. And for them, this is a huge redesign of their deck. And so we never got any traction with the idea. Of course, now we have lots of traction because we're the only ones who make them.
Yeah, Bob, I grew up in the disk drive side of the business. So when I started looking into this and I learned of your flat head profile, I thought it was fabulous. I mean, that was an amazing breakthrough. Because without it, I didn't see how you could have adopted.
I don't see it either.
The disk drive heads.
Yeah, no,
the way you did. Now, so I ask you not to minimize the importance of that contribution, but I'm sure there were war stories to be told about adapting these disk drive heads in terms of the MR elements, then they transition to GMR. Now you're in tunnel MR heads,
We
right?
are, yeah.
And I suspect that the head dimensions are not the same ones as the ones in disk drives. So, for example, in adopting TMR heads, was there any issue with the
So
size
that's
of the width of the head, the track width being so much larger than that of a disk drive, and shorting of heads? And
so it actually turns out that so now that's moving to more recent times, although still years. So in, was it 2008, I had on my chart every year or so, well, probably more often, but we had in January, I'd say, okay, here's what I think we ought to be doing for the future. And in 2008, I had TMR on my slide. We didn't actually get it out the door until 2000, 2 years ago, basically, so almost 8 years. And it was really quite amazing what we encountered in trying to implement TMR for tape head. So in some respects, tunnel valve, it's almost a natural fit for tape head, because what you need is large sensors. Large sensors require a high tunnel barrier resistivity, the so-called RA, whereas disk has little tiny sensors, and by tiny I mean, well, nowadays it might be 30 or 40 nanometers wide, 30 or 40 nanometers tall. They were forced into having to live with heads that were hundreds of ohms, and I think the industry came up with the idea of shunting hard disk heads with just a plain old resistive shunt to bring the resistance down and to make the population of the resistance distribution more consistent for the product drives. But so we didn't really have those problems. In fact, our tunnel barriers are maybe 5 times thicker than an HDD, which is a good thing. So that part was good. The area where we had trouble with TMR is really getting heads. We have these, when we embarked on that, our heads had 32 channels, and of course we need all 32 channels.
Good.
Perfect. No bad ones.
Unlike this.
Yeah, unlike disk, which is you have a bad head, so the slider's a buck.
Right.
The slider's bad, you throw it away, and as long as that's less than not much more over 1%, you're okay. So that doesn't scale well to tape heads. And we actually had that problem in going from AMR to GMR and GMR to TMR. GMR was an interesting structure for tape heads, we learned, and that easily adopted from the disk drive business. Just redimension it, and some of the same things that I was talking about apply. But GMRs have an unfortunate aspect that they have a copper layer, a 20 angstrom copper layer that has to come to the tape bearing surface. We did our best to insulate it, but we did observe that tape heads, you really had to do some heroics to get those tape heads to survive and the GMR heads to survive in the tape environment. We worked our way around it, but when we went to TMR, we were afraid of many things. Like, for example, in a TMR head, one scratch and you're dead. You've got a short and the head won't work. And other things, but it actually turns out in the end that the TMR head was much more suited to running tape on, I think, or at least from a development viewpoint. You have much more amplitude than the GMR, and you're more in sync with what's going on in hard disk drives and so on and so forth. But the interesting thing that we encountered when we were building the heads is that of the 33 heads we'd have on a module, we seemed like we had trouble building heads that didn't have 1 or 2 tracks that exhibited noise, and the noise would show up as what later we learned was jumping between magnetic states, and the states were coming mainly from the domains in the free layer in the TMR structure, And the problem was that we had to learn how to build the hard bias magnets to do their thing. And the junctions that were used in HDD and some of the processes had to be revised in order to get heads that would work and become stable. And I think there was a period of time where I wasn't really sure where that was going to go. I mean, we were working very hard on it, me and a couple other people. And I remember in the course of trying to understand the mechanism of the noise, which was not understood initially by me or our head supplier, I went to Stuart Parkin, who was still at Almaden. And I said, hey, Stuart, I got this tape head, and what is it? Well, it's got 32 channels on it. Yeah, and we're trying to make them TMR, tonal valve. And it was very funny. His response to me was like, well, that'll never work. And I,
very encouraging.
That may be a stock response. I don't really know, but I said to him, I said, well, we have some heads where all the tracks are good. And he said, oh, well, then it does work. But that wasn't helpful. We had to figure out why. But anyway, we were able to sort that all out.
Yeah, the reason I asked you about this is because the folklore in the industry, for those who don't know about tape heads, is that, oh yeah, it's obvious. They just adapted the disk drive heads.
Yeah.
It was a cakewalk. Yeah, it's an obvious thing to do, and my intuition is that it wasn't quite that simple.
Yeah.
That this adaptation required quite a bit of additional. First of all, you ran into surprises. I think you confirmed
at every turn. Actually, I only touched on a few of dozens.
Yeah, and that you really had to modify the designs and processes significantly to be able to adopt these heads, right?
Right.
I mean, maybe I'm wrong, but that's what I would guess really happened.
So we tried to leverage as much as possible what HDD has in terms of process and fabrication and stuff. But in the end, you're right. That everything, it just didn't. It wasn't a direct drop in by any stretch of the imagination, and then there's other issues such as hard disk drive technology moves faster, and we were always many years behind what we needed for tape drives because our sensors and track widths and so on are so much larger. So we found, particularly with GMR, that we had the skills of the people who had done GMR in our supplier had moved on when we needed that skill to kind of figure out what was going on with our heads. So it made that job a little bit tougher. So there were interesting things like that.
We never had hard film magnetic bias in tape heads before this.
Right.
It was all soft film.
Right. And that was starting back in many, 20 years ago. Yeah. Gee, I don't know, Chris, there's so many different things I could talk about, but that
I just wanted to get to properly have you characterize, accurately have you characterize that it was, I don't want to put words in your mouth, but I don't think it was a cakewalk.
Yeah.
That it took some hard work. Like you said, just adopting the TMR took 7-8 years, right? And I imagine there were equivalent battles you fought with the AMR and then the GMR, right?
There were, and we learned, there were, so unlike the disk drive business that employs many dozens of people, we had a group in San Jose, maybe I guess it reached a peak of 20 people. But we're doing the whole entire head integration actuator at that time with Dave Harper. I mean, it was the whole soup to nuts done by one small group of people. So we had to leverage wherever we could, but we also had to learn fast. We had to learn, I guess I should speak for myself, magnetics, magnetic design, head design, how to work with people who lay out, do the HDD process design and things like that. And then how to reorchestrate fab to do what we needed it to do.
And I think you mentioned earlier, were you able to get some significant patents to cover this this area of the
So
technology?
we do. We have a lot of patents, and we've done I think pretty well there. For example, we did patent our implementation of the flathead profile, Jim and I, I mean, one of the things I didn't talk about were all the efforts that we initiated to protect the heads, the tape heads, from the tapes running on them. And so we found that after AMR, that with the advent of GMR, we really needed to come up with a protective coating. And we were not alone in the industry. There were other folks attempting to do the same thing, but there was really nothing available. The heads the coatings that were used for hard disk drive heads, these carbon coatings, would wear off very rapidly in a matter of hours. So we had to find our own strategies for doing the protection, and and we had to make those strategies compatible with the need to maintain head tape spacing and protect against not only wear but corrosion and other effects that come from the tape, which has its own set of chemistries running on the heads, which have their own set of materials.
Are you free to talk about what some of those overcoat materials ended up being?
Yeah, so we certainly, Tom, explored a lot of different things, but what we really settled on was a discovery that we made that aluminum oxide, which you would, or amorphous aluminum oxide, you would normally think of as being a kind of a low-grade material that's in head processing is really designed for etchability and things like that. So as a head coating, it wouldn't be good because it would be too soft and wear off. But we actually discovered and patented a way to form that during the formation of that coating on the head, to have it grow in a polycrystalline manner, which was really quite exciting. So basically what we wound up doing was putting low-grade sapphire on top of the head, and it turns out that had enough wear resistance to provide the kind of protection we were
Get
looking
you
for.
over the threshold of what you needed.
Right, so that was indeed, I think, quite novel. No one was doing that. And probably isn't today. In fact, we're still doing it today. We haven't really ever found anything better than that, and believe me, we've looked.
The big challenge in tape since we moved to thin film heads was just the whole area of pole tip recession, because those materials in that gap are so much softer than the substrate. It doesn't take but a few microinches of recession of those materials, and the head's no good.
Yeah, you end up
So we were
with
battling
an
that.
unacceptable essentially head-to-tape spacing.
Correct. It was defining the head-to-tape spacing almost.
Yeah. So this brings us. I think there was the latest generation LTO. What are we on?
LTO 7.
7. LTO 7
It's a
was.
barium ferrite particle media, and I have no idea what the head is because I left 10 years ago.
Yeah.
It's TMR, right?
It's TMR now, yeah.
And that's about a 40 terabyte capacity cartridge?
It's
or
huge, something like that.
the 20.
20 uncompressed.
Just 20.
Yeah.
And compressed.
Well,
height.
40.
Yeah, okay.
Yeah, 50 compressed.
What's the track pitch now?
So the track pitch in our latest highest density product is 1100 nanometers.
Okay, 1.1
Yeah.
micron.
Yeah.
It's come a long way.
Yeah, sure
It has.
It's almost where
And
disk
we're-
drives were 30 years ago.
Oh, sure, yeah. But,
And the roadmap has, I think, at least 3 or 4 more generations, right? There's LTO,
They're defined through LTO 10. It gets fuzzier and fuzzier.
but I imagine LTO 10 is not a cliff per se, right? It's just, that's however far we could see
I
through
think
the
there's
fog.
a lot of other dynamics in the market right now that are going to dictate the future of LTO. Just having a roadmap really doesn't mean a whole lot anymore. It's really about the survival of the technology. And that relies on the adaptation of the technology by the gigantic data people. And it is making some traction.
It is. Cloud.
Yeah, I
Facebook
imagine
is all
because
in.
as I said at the introduction, I
Google's
don't know of
all
any
in.
invention that is superior to tape in terms of cost per bit and
I think that's correct. Yeah.
archivality, right? So
Somehow tape got a bad rep as being either low-tech or unreliable, which is totally untrue. And all these companies were just building gigantic HDD farms, build a new building, get a whole bunch more cooling in there, and tape just solves that. Because at rest it uses no energy.
I'm curious for your perspective. Over the years, once in a while I would remark that tape technology is basically investment limited, not so much technology limited. In other words, it's not that you can't possibly figure out what to do next, it's that nobody wants to spend the money to do what's obvious.
Very
to do
capital
next.
intensive, yeah.
And do you feel that's still true today? I mean, it's come such a long way. I wonder if it's starting to become very hard now to even if people want to spend the money to move it forward, or do you think there's still a nice runway there for another 10 years of improvements?
My biggest concern is simply that the supply chain. LTO arguably was to increase competition, increase participation. And we got a little traction initially. But the capital intensity of the business has become so large that there's just no other people that want to enter. And if nobody else enters, how long?
Yeah. But this is still a perception problem, because often if you hear somebody in magnetic storage make a comment about it's so capital intensive, it's just how we're going to manage. Compare that to semiconductor. You are nowhere
That's
near.
true.
They spend 10 or 100 times more for an advance than we would need to do in tape. So that kind of tells me, yeah, it's a money problem. People still perceive that it's not worth the trouble.
Well, and I think the other thing is that the other companies that traditionally participated, their tape headlines were just that. They were only for tape heads. So that seems capital intensive to them.
Right.
Where we've got this amortization over the whole acre of HDD equipment. So I did want to mention toward the end of Bob's pitch, I got a panic phone call in the middle of the night once. It said from my old boss and good buddy Kevin Reardon, who said, "I need you in Tokyo yesterday." Which you can almost do that.
Yeah, that's right, yeah.
And
Works better coming this way.
and what it was I didn't really know what the topic was. And I showed up at a bank and it was all kind of like spy movie type stuff, secure doors and badges, and in it was Kevin and 50 Hitachi guys. And they were negotiating the sale of the HDD business. And some Hitachi guy doing his due diligence found out that there was something called a tape head in this deal. And what the hell is that? And why do we want it? And my job was to defend our honor and hopefully not break tape as a result of that sale. And it turns out that they were very delighted once they got her done, because they could make a lot more profit off the tape heads than the disk heads. So they're making tape heads on a disk cost basis,
Right.
but the profit margin's enormous on the tape heads.
Yeah.
So it turned out to be kind of a win-win.
Well, HGST probably in aggregate made no money on hard drives, so whatever you made on tape was very, very good.
Well, in fact, I met the guy who was running HGST
Yeah.
in Almaden, or this area. Forgot his name. He was ecstatic about tape heads. He said, "They're keeping the doors open around here."
Maybe that was Bob Holleran at the time?
It was.
Yeah. Sure.
He was a big fan.
Yep. Good.
But to just go out and invest to make a tape head only line, that would be
Oh, yeah.
prohibitive to You'd have to be a very large company.
Well, yeah, that's what was so significant about this flathead stuff is you enabled all
Right.
of that to happen.
And the TMR, I think, was the
Flathead was
breaking.
huge.
TMR was breaking point for in recent times for those who weren't ready to do it, weren't going to get into it, because the machines to build TMR heads, you know, these Canon and Nelva tools are
Yep.
15
right.
to 20 million each, plus all the infrastructure required to get it working and the
Yeah,
know-how.
if
So
you
if you're
didn't
not
have-
doing it, you're not going to do it.
If you
And
didn't have a
that-
hard disk drive line, you'd probably face a minimum of $1 billion, if not more,
yeah, and
investment, right, to come up with a new line.
Who's going to do that?
I can't imagine anybody entering the
Yeah.
business.
Yeah.
So how long can a single supplier?
Yeah,
There's a lot of brands out there, but people that know.
just one bad business decision and it's all over.
Yeah.
If I were the end user, I would carefully protect this supply source, nurture it. Yeah, it'd be better to have 10 suppliers, right, with independent streams. But a carefully protected small number of suppliers is better than none, I think, given the demand for data storage.
I think the story of tape, it started out as a actual data processing tool, believe it or not. Did a lot of sort merge, database stuff, did some real-time transaction stuff, reconciled the Federal Reserve at night. DLT ended up defining tape for what it really is. Lowest cost,
Storage.
cheap storage. And it's green, which is a huge deal. And given that that's the only parameter that matters now,
It's not the only area in which it matters. Look at solid state storage, right? Whether it's DRAM or flash, it's cost per bit, cost per bit.
well, and people that have criticized the lack of supply chain for tape don't realize that even for solid state and HDD, there aren't that many suppliers. 2 or 3 biggies.
It's basically 2 or 3 at this point.
So it's like the whole storage industry is kind of arriving at this weird place.
So,
Let me ask you a couple more things. Were there any special recognitions given to you as individuals or your people for some of these contributions?
Internally in IBM, there were.
There were.
The LTO, the people involved in the consortia received a corporate award. And then we had people involved. I believe there was another LTO award. There was a corporate award involving engineers. Unfortunately, I don't know if we got you guys.
I don't know specifically anymore. I think we probably did.
I think it
There
seems
were a
like
few-
one of the
There
at
were a
least
few
one.
awards along the years.
Because you start these awards and then every manager that reviews it adds their guy.
True. yeah.
Any external recognition or not yet?
Not to my knowledge. Because we never really did, this was never a real standard. LTO was, it's a licensed de facto standard. We didn't take it to ANSI or ECMA or ISO. So it would be hard for a professional, an external professional organization to
Well, it's a little
recognize it.
bit of an omission, though, on the part of, say, the IEEE Magnetic Society. That's really just dominated by hard disk people.
Right.
They never really thought to recognize any of the interesting things going on in tape over the year. And we expected that and never worried about it. But yeah, there were to my knowledge, no recognition from that route either.
I hope it gets revisited, that possibility, particularly now that LTO is essentially a last man standing, right? I mean, it took over.
Well, there is a
then-
proprietary IBM version of LTO.
No, I
for the
understand,
mainframe.
but it's
Not well known.
and it's rooted, but though in the same innovations, right?
Right.
So
Exact
I
same
think
innovations.
it would be. I hope it does get reconsidered in the near future. For
You know, I think there's some momentum
recognition.
building. For those of us involved in CHM, we get lots of emails generated from the community. Your storage group. Recently, CERN released a wonderful video of how they use tape in their environment. Very well received. Even Microsoft came out and did a very nice thing on tape, featuring tape. And they're even starting to make fun of each other, like Google guys say tape won't work, but they're idiots. It works. And I think there's a renaissance. Okay, I consulted a little bit after I left the business, and I would get asked these, is tape dead questions all the time. And there's an argument out there about which is more important, the metadata or the data. Because a lot of people argue, and there's been books written, that the metadata is really what's valuable. And if you believe that, then you don't need the data. Use it, burn it. But then there are people that argue that the data is more important than the metadata. So if it turns out data wins, that is perfect for tape. Tape is perfect, and it'll be everywhere. It'll go into every social media. I was a customer advocate for the particle smashers. I visited CERN, I visited Los Alamos, and I actually sold that tape to CERN.
Oh, fantastic.
It was
For
funny.
the God
They're
particle,
both
right.
high secure areas, as you can imagine. And at CERN, all the streets are named after famous scientists, Einstein Way and whatnot. At Los Alamos, all the streets are named after islands that don't exist anymore.
So the other side to this too, as a thought I had, is that tape has a pretty good future in terms of areal density. Our tracks are a micron, but we believe we can go much smaller than that. I mean, disk bits are, 30 by 30 or whatever they are, nanometers. So we've got this huge runway. We've got demonstrations that have been done in Zurich for very high areal densities that translate to 200 or 300 terabyte cartridges. They're not doable now. We'll need improvements in actuators and just everywhere you look, but it certainly looks like it's not out of the realm of possible. And then when you look at disk, and of course then where is all this tape going to go? Well, it's going to go into clouds. And when you look at disk, the runway for technological improvements has really become severely limited, I think. Yeah, I mean, HAMR, I don't know if it's ever really become commercialized, maybe.
But yeah, you're right. I mean,
MAMR is the same way.
A factor of 10 at this point is viewed as just a wild dream.
Right,
yeah.
Right. Well, you certainly know more about that than me. I'm working on the patterned media and that, which I think was extremely interesting, but I guess that's, I don't know where.
No, that's not being pursued.
Yeah, it's not being pursued so you really have a technology that has a very good future potentially, provided there's a sustainable investment coming in, which,
But the good news is the demand is continuing to be there, right? I read articles that said the amount of data in the world will double in 2 years. And they project in 2025 it could double daily. I mean, it's...
Yeah, I think, by the way, I think there's a seminar by the local magnetic society.
Do you want to keep it all?
Right, do you want to keep that data, right?
A seminar upcoming next week on the 15th in the evening. The local magnetic society has a seminar on the future of demand for data, right? I think.
Talk about some other applications real briefly. So we talk about the social media, which is really just large amounts of data that you don't need online all the time. CERN uses it when they smash an atom. They have all these gazillion sensors, and they are real time writing that data to tape as it's happening. The European weather modelers can imagine a few square miles of space with 1 millimeter nodes with state variables each. And
yeah, high resolution weather
these simulations are so massive that they insist on saving interim results on tape, so that if something happens, they don't have to start over from zero. They can reload position they were at.
And then there's the teenagers.
Yes.
These guys send videos around the movies like we would
yeah.
send an email.
Yeah,
Right.
yeah.
I mean, and we used to joke about that, remember?
Right,
You
right,
know,
right.
And it's true, videos are just shipped around, you know. Watch them
And
all.
in the Geophysical Society, they'll take a ship. They'll have 40 miles of wire below it, 41-mile pieces, sensor every yard, either temperature, pressure, whatever, salinity, who knows. And they drag it around the ocean, and all of that data goes right on tape, right on the ship.
But then you think of self-driving automobiles, and you know, there's just no end to the demand for data. So to have a scalable technology, right, that will store that, is just incredible, isn't it?
I don't know what would replace it, really.
Yeah.
Before I let you go, you have a vast amount of experience when I add all of your careers. What advice would you give a young person starting today that might be interested in pursuing a career in applied physics and technology and engineering?
Well, I give them two recommendations. One is, of course, follow your passion, what you find interesting. And the second one I've learned over my career is that when you have an idea, you want to go and talk to a bunch of experts who will know all the reasons why your new idea will not work. And then you have to ignore all that and pursue your idea anyway. You don't want to be talked out of something. Because basically the experts know why it won't work, otherwise they would have done it. But it's going to take someone with an idea. It was like self-server, right? We talked to a lot of experts who said it would never work. And they had really good reasons as to why it wouldn't work. But the fact that you could find a way to make it work, right? And I'm sure it's true with all technology, right? Mm-hmm. Stuart Parkin saying it won't work. You changed his mind in seconds, right?
I found that to be very true. There was no greater incentive to make something work than to have somebody say, "We tried that years ago."
Right, years ago.
Yeah,
right.
yeah,
It's never gonna
absolutely.
work.
Yeah, never going to happen. Yeah.
Like predicting the end of aerial density. Remember, there was a talk of all the people that predicted the end.
Yes.
Right. It will never end, right? Human innovation is infinite, I think, right?
But I'm curious what your perspective is. 'Cause I do feel that the golden age of innovation in IT hardware is done. It's not a zero, but there was a wonderful period from, say, end of World War II to the year 2000 where just everything, it was just a wonderful area to be active in. It seems today there's much more stuff going on in software or in bioinformatics or...
Well, you know, it's interesting. The scaling of the transistor might have been the greatest human achievement in mankind, right? Going from 10,000 transistors on a chip to now 10 billion. But as Moore's Law is coming to an end, there's now a whole new renaissance in packaging technology that's taking place, 3D chip stacking. We've just seen announced 3D microprocessor, 2 chips stacked together. Right. If you look at the volume of silicon inside an actual server, it's, you know, parts per million. So I think it will never end. Systems will continue to scale, and you know, the next generation will find a way, right, to do that.
I thought in a way Moore's law in a way made us a little bit complacent, right? Because it was just a matter of very difficult turn of the crank, but all we had to keep doing is turning the crank. But I think now it's getting harder and harder. I think we're going to have to look for some new breakthrough and invest in research that we haven't had to invest in. To create that next breakthrough. But again, I learned very early that you can never underestimate the ingenuity of humans, right? They'll invent some new things that will surprise us.
I always like to remind young students that 250 years ago we were living in log cabins burning wood. We've come a long way in a pretty short amount of time, right? So,
any other advice to young students, John, from your perspective?
Well, nothing specific. I just know watching my daughter and my son-in-law, who are both in the technology industry, they don't intend to have one career. So their model that seems to work for them is a year of this and 2 years of that, and a year and a half of that. And it would be very difficult for me to advise a young person to go into tape drives. I just don't know how I would have that conversation. Or storage, in any storage. So I think it's a follow your passion thing and follow your ideas. So we'll see. I don't think this is stable, but it's hanging on.
Well, I want to thank you all for doing this, and I especially want to thank you for giving me the opportunity to talk to you about it. Thanks again.
You bet.
Very good.
Sure.
Thank you.
Thank
Thank
Our
you.
pleasure. It was fun.